It's my pleasure this afternoon to introduce one of our own alums from our physics department and returning as our visiting assistant professor in physics, Danielle Berg, to introduce Professor Krauss.
Okay, I'm really excited to be up here because I'm a little strange in that I really enjoy a little bit of awkwardness, and I have a feeling that this is going to induce a little bit of awkwardness and excitement in all of us, this talk and discussion to follow. Some of the questions that we are here to ask that we've been talking about is, why is there something rather than nothing? And if space is infinite, what is it expanding into? And is the ideas of multiverses a reality? And why does any of this matter? Our innate human curiosity has fueled our journey of scientific understanding and is why you're all here today. We seek to answer the larger questions of who we are, how we got here, and if we are unique, or rather, what is our place in this universe? The significance of these questions is profound, and it links us to the greater cosmos. As Dr. Filipenko talked about yesterday, in 1998, there were published observations of type 1 supernova that suggested the expansion of the universe is accelerating. Dr. Lawrence Krauss was one of the first physicists to suggest that space is composed of dark energy, making up approximately 70% of our universe by volume. Although we cannot see dark matter or dark energy directly, many of the scientists that are here today and others around the world are looking at its effects on the visible universe. Krauss has gone further by examining our current understanding of the universe in order to ascertain how we got here. By a universe full of stuff such as our own, how could it result from nothing by natural processes? So although we have many spirited young speakers with us today, and even younger Lawrence Krauss received his Bachelor in Physics and Mathematics from Carleton University in Ottawa and his PhD in Physics from the Massachusetts Institute of Technology. He is currently a Foundation Professor and Director of Origins Initiative at Arizona State University. He has published more than 200 scientific articles, many about the physics and astrophysics that we're discussing here. Krauss has also authored several celebrated books, which you can get in the bookmark across the way, hint, hint, including some really great books on the fear of physics, about Star Trek, about the atom, and a universe from nothing. Further, he's the recipient of numerous awards, including the American Association for the Advancement of Sciences Award for Public Understanding of Science and Technology, and the Julius Edgar Lilienfeld Prize of American Physical Society. He was even nominated for a Grammy Award for his liner notes for the Telarc CD of music from Star Trek. This guy has literally done everything. He has even received the Colbert Bump for his book, A Universe from Nothing. In his abundant spare time, he has been working on and created a documentary film called The Unbelievers with fellow renowned skeptic, atheist, and evolutionary biologist Richard Dawkins, which is currently being released in limited cities and I hope to eventually see. The film follows Krauss and Dawkins as they speak publicly around the globe about the importance of science and reason in the modern world. As a science educator and advocate, Krauss is also an active and respected member of the skeptics community. I bring this up because I first heard Lawrence speak at the Amazing Meeting in Las Vegas in 2011. After watching him stand up to a very spirited discussion with Neil deGrasse Tyson on the future of manned space missions, I was a little intimidated, but more so excited and challenged by the controversial ideas Krauss presented. As you may have noticed already during this conference, he is not afraid to voice his opinion, confront disagreement, or initiate thought-provoking discussion. From his exceptional taste in shoes, which you'll get to see in a moment, to being quoted via tweet by Miley Cyrus, or to his impressive IMDb webpage, I cannot think of a more interesting, passionate, or accomplished scientist to engage us all on the universe and its limits. To quote Lawrence Krauss himself, so don't get mad at me, "The amazing thing is that every atom in your body came from a star that exploded, and that the atoms in your left hand probably came from a different star than your right hand. It really is the most poetic thing I know about physics. You are all stardust. You can't be here if stars hadn't exploded, because the elements, the carbon, nitrogen, oxygen, iron, all the things that matter for evolution, weren't created at the beginning of the time. They were created in the nuclear furnaces of stars, and the only way they could get into your body is if those stars were kind enough to explode. So forget Jesus, the stars died so that you could be here today." Whether that quote inspired you and left that awe-induced tingling feeling that I get in my body, or it rocked the boat for you a bit, I cannot wait to see what Lawrence shakes up today and the important discussions that will ensue. It is my great pleasure to introduce to you the sixth speaker of the 49th Annual Nobel Conference and his talk about a universe from nothing, as he challenges what you may think you know about the universe and its origins and ignite your imagination of what lies ahead. Please help me in welcoming a rock star of my scientific world, a man who is obsessed with nothing, Professor Lawrence Krauss.
That worked. Thank you. Thank you, Danielle. Thank you, everyone here, Chuck and everyone else, for organizing this. It's been remarkable. First thing I'm going to do is get off the podium because I don't like podiums. I want to thank Chuck well, first of all, actually, as many of you can know, I like to try and one-up my colleague Frank Wilczek whenever I can, and I want to point out that this is better than his because I won't actually take off my shirt during the talk, so thanks to that. To Chuck, I want to thank him for allowing me to speak sixth after 2 talks on cosmology. So the talk with the universe from nothing, I kind of thought there'd be nothing left to talk about, and I figured that's what he would want me to do. But I'm going to try. I'm going to try anyway. And I think actually I've thought about there'll be some overlap, but Alex's talk and George's talk allowed me to build, I think, on some things that they've said and put them together in a way that I hope will enhance things. And really what I want to do, and this is really what I think all of the speakers have tried to do. It's one of my favorite quotes, and I began at least one of my books with it. I'm also, by the way, not going to use that stupid arrow because I've learned that actually, I checked empirically that you can actually see the screens from the back of the room. So if I do this and this, you can actually see what I'm doing. So it's easier for me to do that. But really, the most exciting part of any mystery is getting to the starting point. And hopefully what we've all done, and what we'll do today and yesterday, is get you to the starting point, because they're wonderful mysteries. And there are young people here who are going to carry on science the next generation. It's those mysteries that should inspire you. The science, we too often teach science as if it was, especially physics, as if it was done 200 years ago by dead white men. And it's not. They're full of mysteries. And I hope that you will be inspired to solve the problems that we've been talking about here today. In any case, okay, so let's begin. The question that Danielle mentioned is an interesting question. And why is there something rather than nothing? It's really inspired humanity since humanity's been thinking about that. How did we get a universe? How did everything we see get here? And it's been the source of constant speculation from religion to philosophy and science. And what's amazing is that science is beginning to at least be able to confront a version of that question. And that does upset some people, as we'll undoubtedly talk about. But what I want to show you is the amazing results that couldn't have been talked about at a Nobel symposium 30 years ago. It's been a revolution in our understanding of the universe that's allowed us the temerity to begin to address these questions, not answer them, but address them. And I think that's what makes it so exciting. Okay, so there are 2 ways to answer that question. One way is to write a book that begins like this. It doesn't tell you anything about anything. And now Frank may think I'm being provocative, but of course I'm really happy to see that my good friend George Coyne agrees with me about this. I really always hesitate to say that George Coyne is a good friend of mine because I'm always worried he'll be excommunicated. But he is. But really, if we want to learn about the universe, the way is not to think about a book written before we even knew the Earth orbited the sun, but to ask the universe. And you've seen this image a lot in different forms, the Hubble Deep Field. But the way, if we want to learn about how the universe might have come into being, and ask those questions because it did come into being. And it's a physical universe, and if we want to address these questions physically, we have to look at the universe and ask the questions. And that's what I want to talk about. And the universe has given us, has changed our picture of everything more in the last 30 years than perhaps the last 2,000. And it's an incredibly exciting time. So, Alex talked a lot about Hubble and the expanding universe. I won't. There are two things I want to add to what he did. One is he didn't mention Hubble's most important characteristic, as far as I can tell, for the young people here especially. Because Hubble gives me hope for humanity. Because he began life as a lawyer and then became an astronomer. And so for all of you who are thinking of law school, there's hope for you after that. That's the first thing. The second thing is, especially with the questions after George's talk, and George happily once again showing us we're at the center of the universe, I thought I might also complement what Alex did a little bit to give you a different way of understanding that we're not. And this is useful, I think, because I often tell students that in physics, the first time you see something, you don't understand it. And the second time you say, oh, I've seen that before. And so and there's a lot of familiarity that helps with that regard. So anyway, this is Alex was kind enough to give me the version of the slide he showed before. This is what Hubble discovered, which is that everything's moving away from us, and we codify it in some relationship that the velocity of objects is proportional to their distance. And that makes it look like we're the center of the universe. And he gave one example, but I'd like to give a different one, which I think, for me at least, helps me understand that this doesn't tell us we're the center of the universe. It tells us that the universe is uniformly expanding. Now, the real problem is myopia. We are actually stuck in our universe. Well, most of us are. The Republican Party clearly isn't today. But you can... But anyway. So the way to see this is to get outside of our universe. And I can draw a universe we're outside of. Here's a universe that has galaxies at regular intervals. And just so you don't feel bad over here, I'll point these. And you can see if you're standing outside of that universe that it's a little bit later, it's expanded. The distance between all the galaxies is bigger. And the question is, what would you see if you lived in that universe? It's quite simple. Just pick a galaxy, any galaxy, say that one. And to see what you'd see, we just superimpose this image on top of this one, placing that galaxy on top of itself. What do you see? Exactly what Hubble saw. And the point is, it doesn't matter what galaxy you pick. There's the image that Hubble saw. Let's take another galaxy, put it on top of itself. Everywhere you are, everything is moving away from you. And that's exactly what Hubble saw. So what Hubble told us is there is no center of the universe, or every place is a center. It depends on how you like to think about things. But really what's important is that the universe is expanding. And the fact that the universe is expanding changed everything. Again, it's so permeated the public consciousness that the universe began, well, except in certain states like Arkansas and Ohio and a few others, that it began 13.8 billion years ago. But the fact that the universe began in a Big Bang is so much a part of popular culture that we forget that less than a human lifetime ago, that was not the conventional wisdom in science. The conventional wisdom in science, and when Einstein was developing general relativity, was that the universe was static and eternal. It had been around forever, and it would be around forever. It seemed reasonable when you looked out at the sky. And so the universe having a beginning changed everything in science, and also, obviously, in philosophy and religion. And it changed everything in science also because if the universe was dynamical, the natural next question was, if the universe had a beginning, how will it end? And Alex talked a little bit about that, and I'll talk more about it. Because if the universe is expanding, the natural question then becomes, will that expansion stop and recollapse in the Big Crunch or something else? And the answer to that question depends. It turns out remarkably, the only way to actually consistently describe an expanding universe is to use the laws of general relativity. Because general relativity is the first theory to describe not just how things move in the universe, in space and time, but how space and time themselves dynamically respond. And what Einstein told us is that space and time dynamically respond to the presence of matter and energy, like curving and potentially expanding. And so what Einstein told us is that the future of the universe depends upon how space responds to the presence of matter and how much matter there is. And we present pictures of that, and I'll show a picture. It's always hard to do, because it turns out our universe, because space responds to matter, space can curve in the presence of matter. And that means it turns out, and Frank gave a beautiful talk on geometry, that our universe can exist in one of three different geometries, so-called open, closed, or flat. Now, it's hard to picture these. As Frank was pointing out, it's hard to picture a four-dimensional universe in general. It's hard to picture a curved three-dimensional universe because we live in a three-dimensional universe. So we draw pictures, two-dimensional pictures to guide the eye, but that's all they are. So here, it turns out in 2 dimensions it's the same thing. You can have a closed universe, which is a surface of a sphere in 2 dimensions, a flat universe like a piece of paper that's flat, or an open universe like a saddle. But these just guide the eye. In a real closed universe, we're talking about the curvature of 3-dimensional space. And you can't picture that easily. You can write it down mathematically. We can talk about what it would seem like. For example, in such a universe, if you looked far enough in that direction, you'd see the back of your head. Okay? So we could talk about that, and it all sounds very nice, but what's really interesting, and the reason physicists cared about that, in fact, the reason I got into cosmology, because I got into cosmology because I wanted to be the first one to know how the universe would end. It seemed like a good idea at the time. And the answer depends upon, based on general relativity, on the amount of matter. Because if there's enough matter, and we live in a matter-dominated universe alone, then if you have enough matter to make a closed universe, while that looks nice and it's wonderful to talk about at cocktail parties, the important thing is, in a matter-dominated universe, the universe will expand to a maximum size and then collapse. In an open universe, it'll go on expanding forever. And a flat universe is the boundary between the two, where it slows down and never quite stops. And so the real question of 20th century cosmology became, which universe do we live in? Because then we know what the future will be. And if we want to know which universe we live in, we have to know how much stuff there is. Very simply, we just have to weigh the universe. It's a homework exercise. And that really, weighing the universe, became the business of 20th century cosmology, and I've written books about it. And you can talk about it for a long time, but like many things, a picture is worth 1,000 words. But I want to give you a perspective. We have weighed the universe, and I'll show you the results. To give you a perspective on this, I want to take you back a little time in history, I think, especially for the students. Some of you will become scientists, and you'll submit articles to journals like Science, and you'll be rejected. Okay? And I just want to tell you, you shouldn't worry. I want to take you back to a kindler, gentler time. It's a much more difficult time than it used to be. So I want to take you back to 1936. And there was an article that came out in Science magazine called Lens-like Action of a Star by the Deviation of Light in a Gravitational Field. And here's how it began. Some time ago, R.W. Mandel paid me a visit and asked me to publish the results of a little calculation which I had made at his request. This note complies with his wish. Okay? Try that now and see what happens, okay? So, I mean, now the author had credentials. His name was Albert Einstein, so it kind of helped. But what Einstein published there was the results of a calculation that he thought was completely unimportant. So unimportant, he wouldn't have published it otherwise. He published results of a calculation. He'd earlier showed that light curved around a massive object. That's what made him famous, as was pointed out. But he realized if you had a massive enough object and you had a source of light behind that massive object, then the light could curve in both directions and come back and converge. And the object could act like a lens. It could magnify objects like my glasses do for nearby objects. Or if I had a cut glass goblet, which you don't have here, I could look through that and I'd see many images of you. But he thought it would never be observable. He thought it was totally unimportant. In fact, it's kind of interesting. If you look at his calculation from his notebooks in 1936, you also realize that this is the calculation on which that's based, that actually he'd done exactly the same calculation in 1912 in his notebooks from 1912. He just forgot he'd done it. Okay? And my favorite part of this whole story is the note he wrote the editor afterwards. He said, "Let me also thank you for your cooperation with the little publication which Mr. Mandel squeezed out of me. It is of little value, but it makes the poor guy happy. Okay? That's how science is done, okay? And the great thing, of course, is he was totally wrong. It's not of little value. It's the way we weigh the universe. And here is the picture of the very phenomena that Einstein said would never be observable. And Alex showed a different one, but this is relevant. This is an amazing picture because it's a picture of gravitational lensing. It's a picture that results from the fact that space is curved. So you don't have to be a rocket scientist, as Sam Ting would say, to see that this is a cluster of galaxies. And as George pointed out, clusters of galaxies are the largest bound objects in the universe, maybe almost 10 million light years across from side to side. They're the biggest bound objects in the universe, and anything that can fall into anything will fall into a cluster. So if you can weigh the clusters, you can weigh the universe. And like many of the images you've seen before, every dot in this picture is a galaxy, not a star. Each of these galaxies contains hundreds of billions of stars. This is a cluster that's 5 billion light years away. 5 billion light years away. So the light from those stars left before the Earth even formed. Okay, and by similar token, if there were beings on that cluster that looked at us and saw the light that's happening now, we'd long be gone by the same time they watched. And in fact, most of the stars in this image may not even exist anymore. They may have ended their lives. And the civilizations that may have existed around them and had meetings like this are no longer. And I mean, I think that's really important because we may talk about spirituality, but this is real spirituality. When you look at this, images like this, they inspire you in ways that nothing else I know of can inspire. But in any case, as inspiring as that is, the really important thing is you don't have to be a rocket scientist to see that these blue things here are different. And what they are multiple images of a single galaxy located 5 billion light years behind that cluster. A galaxy that's so faint that without the magnification of that cluster, we probably wouldn't have even seen it. But not as only just one image, there are many images because the cluster, as a glass goblet would, splits up the light. It bends in many different directions. So this is proof, if you wish, that space is curved. But we don't need the proof because we know general relativity works. We test it in many other ways. So now, as Frank talked about, we can now use it to test other things. And so we use general relativity. And the point is, now that we know general relativity works, we can use it to weigh this cluster. Because you can ask how much mass must there be in that cluster and where is it distributed in order to produce the image we get. Now that's a complicated thing called a mathematical inversion. It's relatively complicated to do, but you can do it. And Tony Tyson and others a long time ago at Bell Labs did it. And here is this cluster, and this is where the mass is as extracted from. In order to produce the image that was seen, the mass must lie in this direction here, in this way. And of course, what you can see is spikes where the galaxies are. But really, what's most important is you see a huge mountain of stuff where the galaxies aren't. There's 40 times as much mass in this picture as meets the eye. Most of the mass is where the stuff isn't shining. And in fact, around each galaxy, there are little mountains as well. Most of the mass associated with each galaxy is not visible. And that's the stuff that physicists, with their great linguistic perspicacity, have called dark matter. And so we know that there's 40 times as much stuff in here, and it's dark, it doesn't shine, but what makes it particularly exciting, and one of the reasons we're talking about it, is for reasons I won't have time to go into, maybe in the question period, I don't know. We have many good reasons to believe, not to believe, to understand that there's too much stuff there to be accounted for by all the protons and neutrons we know are in the universe. We know how many protons and neutrons are in the universe, and there's 10 times more of this stuff than is allowed by that. So that tells us that it's probably not protons and neutrons. That means it's some new type of elementary particle of the type we talked about, and Tara was talking about discovering at the Large Hadron Collider. And what makes that particularly exciting is that means we don't have to just look out there through telescopes for it. It's in this room. It's going right through your bodies as you nod off after lunch during this lecture. And that means we can build experiments to look for it. We don't have to use telescopes. And where do we build the experiments? Not here, because right now we're all being bombarded by cosmic rays. That would, if you put an experiment here, it would just have too much noise. You go deep underground. because most of the cosmic rays will be absorbed. But these dark matter particles, because we think they interact so weakly, most of them will go right through the Earth without even knowing it was there. And there are experiments being built around the world to look for that. Actually, takes me back. This is actually based on a proposal that Frank and I made 25 years ago or so, and then we didn't have to build it. So, but this is a dark matter detector that's actually located in Minnesota, deep underground. And it's kind of simple. You just take a little bit of germanium here and cool it down to about 1/1000th of a degree above absolute zero, which is what I'm told it is here in the winter. And then what happens is most of the dark matter particles will go right through the Earth without even knowing it's there. But every now and then, if we're right, one of them may bounce off a nucleus of germanium, and it'll heat the whole thing up roughly by 1/1000th of a degree. And so you put the whole thing underground and you try and shield it from radioactivity, and you hope maybe once a year, once a decade, once a century, you'll see a blip that can't be explained by anything else, and that might tell us the nature of the dark matter. And as I said after Tara's talk, the interesting thing is there's a race between the Large Hadron Collider and experiments like this to see if the dark matter is made of this stuff. One or both should see it, and that's incredibly exciting. But it turns out it doesn't matter what it is. Again, as I think Frank mentioned afterwards, it doesn't matter because we just want to know how much of it there is, because it's its gravity that will determine, we thought, the future of the universe. So let's go back to this and say, how much stuff is there when we weigh the universe like this? And we've come up with the answer. After 80 years, we've come up with the answer, and I'm going to show it to you. A drum roll. Okay, whatever. And there it is. Okay, there are people back in the room that are fainting right now. When physicists have an important number, we always give it a Greek letter to sound scholarly. And omega, which George alluded to, is a very important quantity. Omega, we call it's a quantity that defines for us the ratio between the actual amount of matter in the universe and the amount of matter to make an exactly flat universe. So if omega is less than 1, the universe is open. And if omega is greater than 1, the universe is closed. And you can see here, even from a long time ago, that at high accuracy, and the numbers have gotten better, there's only 30% of the amount of stuff to make a flat universe. So it looked like we got the Holy Grail. We'd finally figured out the universe is open, end of story, no need to have talks and such, etc. But there's a problem. The problem is we theorists knew the answer, because we always know the answer. We're not often right, but we always know the answer. Okay? And we knew that the universe was flat, because a flat universe is the only mathematically beautiful universe. And here these darn observers were doing what observers do so well, which is get it wrong, we thought. But there's clearly a loophole here, which is this determines how much stuff is around galaxies and clusters of galaxies. But what about all the stuff where there aren't, all the regions where there aren't galaxies? Clearly there's huge ways of missing stuff. And this is a very weird way of determining the geometry of the universe, because this really tells us the geometry of the universe, we thought. Because you have to plug the matter into Einstein's equations and then solve Einstein's equations, measure other quantities like the expansion rate of the universe, plug it all in, and from that try and infer the geometry of the universe. Wouldn't it be better to measure the geometry of the universe directly? And what's amazing is that we can, and we have been able to, and I'm thankful to George in some sense that he didn't talk too much about it, so I can. We have been able in the last decade or so to measure the geometry of the universe, which is just remarkable in the extreme. Now, how would you measure the geometry of the universe? Especially if let's ask how you could measure the Earth is curved if you couldn't go around it or you couldn't go into a satellite, okay? If you just lived in Kansas, how would you know the Earth is curved? Well, very simple. You draw a triangle, and you ask a Gustavus Adolphus student what are the sum of the angles in a triangle. You ask anyone else, and they won't know. But it's 180 degrees, but I'm assuming that they have a good education here, I can tell. And that's fine, because we all learn our geometry from Euclid, as Frank pointed out. But in fact, on a curved surface, it's quite different. And in fact, he showed a slide about that. But on a curved surface like the surface of the Earth, I can draw a triangle as follows. I can go along the equator, then I can make a right angle and go up to the North Pole, and then another right angle and go back to the equator, and I got a triangle with 3 right angles. 3 times 90 is 270, and 270 is 180. So if I draw a triangle that was big enough on the surface of the Earth, I could prove the Earth is curved. And what is truly amazing is that same thinking works not just in 2 dimensions, but in 3 dimensions. If you could find a big enough triangle in our universe, you could measure the curvature of the universe. And that's what we've been able to do. People were trying for a long time. And we've been able to do it with the cosmic microwave background radiation that George so beautifully talked about. I remind you from George's talk that when we look out at the cosmic microwave background radiation, we're looking back at a time when the universe was a few 100,000 years old. Back to the moment when it became transparent. Now, seeing the images of that baby universe, and I'll show a different version of it, is amazing. It's worth a Nobel Prize or 2, in fact, at least 2. But what's equally interesting is there's a very important scale on that surface, and that's 1 degree. Because 1 degree represents, in general, in certain cases, and in a case that I'll talk about, 100,000 light years across on that surface, approximately. And if the universe is about 100,000 years old, Einstein told us that no information can travel faster than the speed of light. And if that's true, nothing on this surface over here could affect anything at that surface over there, because that's how far light can travel in the history of the universe. Okay? And certainly at that time that surface was created. Now that sets an important scale. Because if I have a lump of matter that's smaller than that scale, what does that lump of matter do? As George pointed out, it collapses. And then it heats up and it does all the sort of things that lumps of matter do. But if I had a lump of matter that's bigger than that scale, it doesn't even know it's a lump. It's like, I used to watch a lot of TVs. It's like Wile E. Coyote on the Roadrunner. If you remember, he used to run off a cliff and then he'd hang around a while before he realized he was supposed to fall. And that's exactly what would be the case. Lumps bigger than this don't know they're supposed to collapse. So the biggest lumps that can have collapsed or begun to collapse the moment the microwave background universe becomes neutral, when things can begin to collapse, as George pointed out, the largest lumps that can collapse are that big. But that creates a ruler for us. It creates a ruler that's 100,000 light years across. Well, let me just go back for a second. So that's a ruler, and it creates a triangle. We can ask, how big are the largest lumps? And to go back to this image, this is, again, I think something that Frank's slide showed, in a flat universe, and by the way, a flat 3-dimensional universe is not a pancake. It's just the universe you always thought you lived in, where the x, y, and z axes point in the same directions everywhere in space. Okay? In a flat universe, light travels in straight lines, and a 100,000 light year across ruler or lump should span on our eye 1 degree. But in an open universe, where light rays diverge as you go back in time, the angle spanned by 100,000 light year across ruler will be smaller. The ruler, the lump, will look maybe half a degree across. And in a closed universe where light rays converge as you go back in time, the ruler will look bigger. So all we have to do is take a picture of the types George took and ask, how big are those biggest lumps? And that's what we've been able to do. And the first experiment that began to really address this was not a satellite experiment. It was a ground-based experiment. It was in Antarctica. The boomerang experiment, it was called. Here's a balloon and a microwave radiometer, and it was sent up above the Earth to be able to look carefully at a small region of the sky. And that balloon went around the world, which is, of course, easy to do in Antarctica. If you're at the South Pole, you just do this. But it wasn't there. It was at McMurdo. So it took about 2 weeks to get around and come back to where it began. Well, it was called boomerang. And then it took this image, which superimposed on the original image. Here are the hot spots and cold spots of the type that George showed, as observed first by Colby and then much higher detailed by other satellites. But here they are. And the question is, these are the primordial lumps, as he pointed out, that were created at the very beginning of time, that would later collapse to form everything we see. The galaxies, the stars, the planets, etc. But the important question is, how big are they on average? So to see that, we can create universes in a laboratory. And on a computer, I guess I wanted to show the Planck picture just to show we do much better now, but I figured George would show it. And here's boomerang. Here's that same region of the sky it looked at in a different false color image. And here are universes on the computer. We create a closed universe, an open universe, a flat universe, and we ask how big on average would those lumps look? And in a closed universe, the average 100,000 light year across lump would look that big, but that's bigger than these lumps. In an open universe, the average 100,000 light year across lump would look that big, but that's smaller than these lumps. But just like Goldilocks, in a flat universe, it's just right. And in fact, we now know to an accuracy of perhaps better than 1% that the observable universe is flat. So if you're a theorist, you can do this. Okay. Well, you shouldn't pat yourself on the back too much because, of course, there's a problem here, which I hope you're aware of. A few minutes ago, I proved the universe was open. We've only measured 30% of the amount of stuff to make a flat universe. And so there's a big problem. Well, if the stuff isn't where the galaxies are, it must be where galaxies aren't. But what is where galaxies aren't? Nothing. Now, the amazing thing is that we have learned, one of the great developments of 20th century physics, is that nothing is not so simple. When you put together the laws of quantum mechanics and relativity, then empty space becomes a dynamical thing, much more dynamical. When you put together quantum mechanics and special relativity, it turns out that there must be, that the empty space is really a boiling, bubbling brew of virtual particles that are popping in and out of existence in a time scale so short you can't see them. Particles we call virtual particles. Now that doesn't sound very impressive. It sounds like counting angels on the head of a pin. Okay? But so, the purpose of science isn't to invent things you can't see. That's the purpose of other things I won't go into at the moment. But so if you can't see them, then how do we know they're there? We can't see them directly, but we can see their effects indirectly. In fact, they're required and an essential part of understanding of modern physics. This image, which all of you have been staring at while I've been talking, I see, was actually something that Frank showed at the Nobel Prize ceremony. It's actually, while it's an animation, it's more than just that. It's based on real calculations. This is what the empty space inside of a proton looks like. Now, if you went to a good high school, and I'm sure the students here did, you learned that protons are made of 3 quarks, right? Okay. Well, we lied. Okay? They're not. They are made of 3 quarks, but it turns out if you add up the mass of those quarks, they account for almost very small percentage of the total mass of the proton. Most of the mass of the proton comes from the fact of these virtual particles popping in and out of existence, these fields giving energy and mass to the proton. So maybe 90% of the mass of the proton or more is due to these virtual particles and fields. So you wouldn't be here if those virtual particles didn't exist. That's how important they are. So, and in fact, Frank won the Nobel Prize for the theory that allowed this calculation to be performed. So if we have a theoretical basis for calculating the contribution of virtual particles to the inside of the proton, why not apply the same ideas to empty space and ask how much energy would these kind of virtual particles give to empty space? And that's where you come up with the result that Alex mentioned. I notice kindly the 1 is missing from here, but if we do the same kind of calculation, we estimate that the energy of empty space is roughly a gazillion times the energy of everything we see. It indeed is the worst prediction in all of physics, although maybe some of my colleagues here have made worse, I don't know. But what we know is that the energy of empty space cannot be much more than the energy of matter, or we wouldn't be here. And so this problem has been around since before I was a graduate student, but certainly when I was a graduate student, and since then, which became called the cosmological constant problem. Why should the energy of empty space not be 120 orders of magnitude larger than everything we see? And as I alluded to in the panel earlier, we were able to go to sleep at night because we knew the answer, because we're theorists. And we knew the answer had to be exactly 0, because 0 is a beautiful number. More than that, there's other more relevant physics reason. If the energy of empty space was not going to be bigger than the energy of everything we see, we'd have to cancel this big number to 120 decimal places, leaving a non-zero number in the 121st decimal place. No one knows how to do that. But 0 is a number we know how to get in physics. We have mathematical symmetries of the type Frank talked about and others they're mathematical symmetries that might cancel things exactly. So we all went to bed at night knowing that there was some symmetry of nature that would cancel things exactly, and the answer was 0, and so we didn't have to worry about it. But physics is an empirical science. And as I will argue in a bit, the universe doesn't give a damn what makes us happy. And so what we really want to know is that really the case? And the only way to do it is to observe it. Now, it turns out if you put energy in empty space, as has been alluded to in general relativity, it is remarkably gravitationally repulsive. All the people who've taken physics here know that gravity sucks. Okay? But in fact, for empty space, gravity blows. Okay? And that is remarkable. And that means if you look at the expansion of the universe, over time, if the universe is dominated by the energy of empty space, the expansion of the universe will speed up, not slow down. Now, as Alex talked about, in 1998, several groups of astronomers were trying to measure not that the universe was speeding up, but they were trying to measure the rate at which the universe was slowing down, because that's what a sensible universe should do. And to do that, they had to measure very carefully the expansion rate of the universe. And I just want to show, understand how much better the things are with type 1a supernovae of the type that Alex talked about. Here's Hubble's original data on the expanding universe from 1929, velocity versus distance. This is one of the reasons he was such a great scientist, because he knew to draw a straight line through that data set. And it's not so obvious. And he also did something else that astronomers have depended upon ever since then. He got the answer wrong by a factor of 10. They've tried to emulate that. He didn't do it because he was a bad astronomer. He did it for precisely the reasons that Alex talked about. To measure velocity and distance, you have to know the distance of objects, you have to have a standard candle. And it's very difficult to get standard candles, and the type 1a supernovae that he talked about have changed everything. Here's that picture he showed. I love this picture. It's of an exploding star as bright as a galaxy that's about 90 million light years away. And one of the other things I want to do just to add to what he said, to maybe emphasize this point, is that we can use these things. And here's a nice movie made by one of the two groups that he worked for. This is an exploding star. You can see its brightness over time and its colors, and it'll keep reproducing over time while I talk about it. The amazing thing is that you can do this, and he alluded to why, using statistics. But I want to just emphasize it from a slightly different perspective. If you went out tonight, and it's a clear night, and you held up a hole in your hand about the size of a dime, okay, where you couldn't see any stars, with the largest telescopes in the world of the type he showed, you could see 100,000 galaxies in a region that big. And if you do the calculation, once per 100 years per galaxy, if you can see 100,000 galaxies in a single image like that, you're bound to see a star explode, and people like him apply for telescope time to do just that, and they do it. And it's amazing. It's an important lesson. The universe is big and old, and rare things happen all the time. Another lesson that I think has implications in different contexts, as we'll talk about. Things sometimes just happen, even if they're very strange. Okay. This is to show you how much better you can do now. This is a modern Hubble plot with the type 1a supernovae. This was, of course, developed after the profound mathematical discovery that on a log-log plot, everything's a straight line. But still, aside from that guide to the eye, we can now use that to measure the Hubble constant to an accuracy of better than maybe 5%, not a factor of 10, as when Hubble got it wrong. And that allowed these groups, as he pointed out, to produce result, and this is actually, there was the cover of Science was shown, but then afterwards, this is the two groups' data. This is the Hubble plot, this is the distance versus velocity, and the question is, what happens to it at very far distances? Does it turn up or turn down? And the way to see what happens is to draw a straight line through that data set and make the whole thing horizontal. So a straight line would be a horizontal line here. And what they and the both groups were looking for was to see how these distant supernovae would follow this curve going down, because that's what a sensible universe should do. And what they discovered, to their amazement, is that the supernovae didn't even lie below the straight line or on the straight line, they lay above the straight line. And there's two explanations of this. One, the data's wrong, which it usually is, but in this case it isn't. And two, empty space has energy, and the universe is accelerating. Now, if just for fun you try and fit the data and ask how much energy would you have to add to empty space, fitting the data, you get exactly what we were missing. If you put 70% of the energy of a flat universe in empty space, everything works. That's another reason why scientists are so quick to accept this result. Not just because it was a convincing result that the universe was expanding. There were lots of things that might have suggested that was wrong. But the universe is flat, only 30% of matter, and this fits exactly. So that is the cockamamie universe we live in. That is a profound result. We live in a universe, a flat universe, in which 70% of the universe is dark energy, this stuff the energy of empty space. Almost 30% of it is dark matter, and a little bit of cosmic pollution. Actually, 1% of it is what we can see. It's true that it was mentioned to be 4%, but most of that isn't even visible. If you look at the universe that we can see, if you take all the stars and galaxies and everything you can see on a beautiful night here in Minnesota and get rid of it and us and everything, the universe would be largely the same. So much for a universe made for us. We are a little bit of cosmic pollution in a universe of dark matter and dark energy. And it's changed everything, and I want to spend the rest of the talk talking about the implications. So let me summarize. The dominant energy in the universe resides in empty space. We don't have the slightest idea why it's there, and I want to remind you, we do not have the slightest idea why it's there. And in deference to my good friend Jim Gates, if anyone comes here and tells you they understand it, they're lying, especially if they're a string theorist. And its existence is tied, we think, to the very nature of space and time and to the origin of our universe, which is why it's so interesting to us. And as Alex alluded to, but I'll describe in a little more detail, it will determine the future of the universe. In fact, the reason I got into cosmology was the wrong reason, because it turns out geometry is irrelevant. It doesn't matter whether we live in an open, closed, or flat universe. The future of the universe is determined not by geometry, but by the energy of empty space. Okay. Now, I was going to ask for your apple. I meant to ask you, Alex, for it. But pretend I have Alex's apple here.
You want a ball?
No, it's okay. I'll just, this is good enough for me. It's more likely I'll catch it. So if I want to take you back to one of your favorite times in high school, which is high school physics, okay? We teach high school students how to calculate what will happen when I throw a ball up in the air. If I throw it up, as you pointed out, it'll come back down. If I throw it up faster, it'll come back down a little bit later. And if there's no ceiling, if I throw it really fast, it won't come down at all. And here's how we do the calculation. We turn it into bookkeeping. We say that the energy of an apple has two pieces. We call it the kinetic energy and the potential energy. It doesn't matter. There's a positive piece, which is the energy of motion. There's a negative piece, which is due to the gravitational pull of the Earth. And it just becomes bookkeeping. If the total energy, sum of the two energies is positive, the coin will escape. If it's negative, it'll come back to Earth. And that's what NASA uses every time they try and figure out how fast to throw a satellite up into space. Okay? But the remarkable thing is we can use that to discuss the universe as a whole. Because if it's expanding and it's the same everywhere, then what happens to every galaxy in the universe will happen to any galaxy. And therefore, if we take a region where we're at the center and ask what's going to happen to the universe, we just have to look at one galaxy that's moving away from us, and if it stops and comes back, then they all will. And then the calculation becomes just like an apple. We want to know the two pieces of the energy of this thing. The positive piece depends on its speed away from us, but that's what Mr. Hubble and others have told us. That's the positive piece. The negative piece comes from the gravitational pull of all the stuff inside, including the dark matter that we've discovered. So all you have to do is compare those two things, and you can determine, in a matter-dominated universe, the future. Okay? Now, the interesting thing is, if the negative piece beats the positive piece, if B over A is bigger than 1, then that region will collapse again. If B over A is less than 1, the universe will expand forever. But what is truly remarkable is we now know, in a cosmic sense, that B over A is nothing other than that quantity omega, which we've measured. We live in a flat universe. Omega is 1. And if omega is 1, then B over A is 1. And if B over A is 1, then B is equal to A. But if B is equal to A, the negative piece equals the positive piece, and that means the total gravitational energy of every object in the universe is 0. Now, if you were going to make a universe from nothing, what would you make the total energy? The first idea that maybe you can have a free lunch. And in fact, as Alan Guth has said, the universe is the ultimate free lunch. So now let's go to this question. Why is there something rather than nothing? The first answer to that, well, we have to be a little careful and describe what we mean by nothing. So the first kind of nothing is, say, the nothing of the Bible, of an infinite void, a dark, infinite, empty void, empty space. Well, that kind of nothing, it's easy to get something from. In fact, it's impossible not to, because that kind of nothing is unstable. This is what nothing looks like. We've seen it. It's virtual particles popping in and out of existence. Well, that's not real stuff. How can you get 100 billion galaxies? Well, when you add gravity to the mix, the reason these particles pop in and out of existence in such a short time is something called the Heisenberg uncertainty principle. When you take particles and you pop them into existence, they have energy. But if they stayed there, they'd violate energy conservation because there wasn't anything there to begin with. So they have to disappear before you can see them. Quantum mechanics is kind of like the White House in corporate America. If you can't see it, anything goes. But when you have gravity into the mix, then these particles can have gravitational attraction, which produces a negative energy. And the total energy of the particle-antiparticle pair that pops into existence could be 0. And if that's the case, those particles can exist with impunity. There's no violations. And so you're guaranteed if you wait long enough in a universe that survives long enough, empty space will start spewing out particles. And you can get 100 billion galaxies worth of them if you had to. There's nothing that violates any of the known laws of physics to get something from nothing. You don't need supernatural shenanigans. Okay. Well, some people would say that that's not nothing. Because, after all, where did the space come from? You got the particles, but where did the universe come from? Well, the interesting thing is, and we don't have a theory of quantum gravity, I want to emphasize that. We do not have a theory of quantum gravity. Okay? We're working on it. Many people are, and many people think they have hints of it. But one of the things we know about any theory of quantum gravity is it's quantum mechanical. And quantum mechanics tells us that in space, particles can pop in and out of existence. Quantum fluctuations can happen. Gravity is a theory of space and time. If we quantize that, then space and time become quantum variables, and space and time can pop in and out of nothing. And I think Frank showed a picture which some people would, in different versions, could say is just that. Any theory of quantum gravity, when you put gravity and quantum mechanics together, it allows spaces and times to pop into existence. It means that there's no space, no time, and poof, a universe pops into existence. Now, most universes that pop into existence will pop out of existence, just like virtual particles, okay, in a microscopic time. What kind of universe could exist with impunity? A universe with 0 total energy. Now, it all begins to sound like it's all coming together, but it's not so simple, and I don't want to pretend it is. Because it turns out the only universe that we can actually mathematically prove has 0 total energy is not a flat universe, it's a closed universe. So what gives? Well, most closed universes, as you saw, will expand and collapse, and they'll expand and collapse if they created microscopically in a microscopically short time. The only closed universe that would survive long enough for us to ask the question is one in which there was a very early period of accelerated expansion that would puff it up so large that it wouldn't collapse right away. But that's precisely what particle theory now predicts. This theory we've heard mentioned several times, called inflation, predicts naturally, based on extrapolating the kind of physics we talked about, that very early on in the universe, there was a period of accelerated expansion when it increased inside by a volume of at least 10 to the 90th in a time frame of a millionth of a billionth of a billionth of a billionth of a second. It sounds like science fiction, but it's not. Now, what will that do? Well, what would inflation do? If it happened in the early universe, it would take a closed universe and puff it up. But if it puffs up, what would happen? Well, it's like puffing up a balloon and making it the size of the Earth. When you puff up a universe that's curved, you make it look flatter. And therefore, the only closed universe that could survive long enough to be enough for us to evolve, still can use that word here, is one that had an inflationary period, and therefore one that must look flat. So in fact, the only universe that can be created from nothing by this kind of mechanism and survive long enough for us to be around is a universe that looks flat, precisely like the universe we live in. And that's the point I want to mention. We can't show, because we don't have a theory yet, that the universe came from nothing by this. But it's plausible. And that plausibility is amazingly worth celebrating. But more than that, we can ask the question, what would a universe look like if it was created from nothing by just laws of physics without any supernatural shenanigans? and it would look exactly like the universe we live in. And that is remarkable. But that's not enough. Because some people would say that's not nothing. Because you don't have particles, you don't have radiation, you don't have space, you don't have time. But what about the laws? What about the laws themselves? Well, it turns out that even the laws of physics themselves may be accidental. And to do that, I want to answer the question Sam asked, actually, in the panel a little more rigorously. And Alex alluded to. It's this amazing coincidence. This is a brief history of time. That's the last, as George would say, it's the last complicated picture I'm going to show you, so it's downhill. This is the density of matter in the universe as the universe expands. The density goes down. This is the density of empty space, energy density of empty space. It remains constant. And we live in a time, 13.8 billion years after the Big Bang, when the energy of empty space is roughly 3 times the energy of matter. That's the present time. But when you look at this, or when physicists look at this, they go crazy if you stare at it long enough. Because Copernicus told us it's not supposed to be this way. Why should we live? We live in the only time period in the history of the universe when these two numbers are about the same. When the energy of empty space is almost the same as the energy of matter. Why should that be the case? It's not supposed to be the case. There's nothing special about 13.8 billion years. There's nothing special in the fundamental constants. We should just live in an average time. Why are we living in such a special time? Well, physicists have thought a lot about this, and one of the answers is here. Galaxies exist, as was pointed out, and I want to explain that. Let's say the energy of empty space were 50 times greater. So that line, instead of being here, was up here. Well, then these two curves would cross at a different point. They'd cross, in this case, at the point when galaxies first formed. But if the energy of empty space was greater than the energy density of matter before galaxies formed, galaxies wouldn't form, because the repulsive force would beat out the attractive force. So if the energy of empty space were much bigger than it is today, galaxies wouldn't form. And that's led some physicists to something I like to call, well, anthropic mania. The argument is perhaps there are many different universes, and the energy of empty space is just a random variable. It changes in each universe. Then only in the universe in which it's not much greater than we measure today will galaxies form. And only then will stars and planets form, and only then will astronomers form. So the universe is the way it is because there are astronomers here to measure it. It sounds funny. It sounds almost religious. It sounds like purpose. But it's not. That's a mistake. It's the same mistake you make if you assume the fact that bees can see the colors of flowers is because they're designed to do so. That's due to evolution and natural selection. This is a kind of cosmic natural selection. We would be amazed to find ourselves living in a universe in which we couldn't live. That would be worth writing a book about. So it may just be a remarkable accident associated with our existence. That the reason we find this value is that if it were different, then we wouldn't be around in our universe. It's awful, of course, because it turns physics into environmental science, God forbid, but nevertheless, it may be true. But particle physicists have jumped on this because particle physics is way ahead of cosmology. There are many more problems we haven't understood for much longer than cosmology. We don't understand why gravity is the weakest force in nature. We don't understand why the proton is 2,000 times heavier than the electron. We don't understand why there are 3 generations of elementary particles. Those are the kind of things that Tara and her colleagues are trying to address with experiments, and theorists are also trying to address. So some physicists have jumped on this and said, this is great. We don't have to understand anything. Maybe it's all an accident. Maybe it's just, if it were different, we wouldn't be here, and then we don't need a theory of everything. We just need a theory of anything. But we have such a theory. It's called string theory. So I want to give, before George, Jim may give a longer version, but I'm going to give a short version of string theory. So this one guy says to another, I just had an awesome idea. Suppose all matter and energy is made of tiny vibrating strings. The second guy goes, okay, what would that imply? The first guy says, I don't know. So that's a history of string theory over the last 40 years or so. And it's had its good times and bad times. But one of the things that nevertheless, and it's a well-motivated theory, I don't want to make any more fun of it, but one of the problems and opportunities, I suppose, of string theory is that it, in general, requires many more dimensions than the ones we actually see and measure, 10 or 11 in most of them. And the question is always, where are those dimensions? We don't see them, and one way to get rid of them is to curl them up into very small volumes. But what's amazing is every different way you curl up those extra dimensions in string theory, you end up with a residual universe with different laws of physics. And so some people realize there may be 10 to the 500 different possibilities. Even if there's only one string theory, there may be 10 to the 500 different four-dimensional universes that could result, each of which would have different laws of physics, depending upon how you compactify these extra dimensions. But then, you see, then you're guaranteed to find a universe like ours. Because in each universe, there could be different laws of physics and the different energy of empty space. One of them is bound to look like ours. Now, is that science? I mean, if you have something that's consistent with any possibility that could ever arise, it's an interesting philosophical question, whether you have a scientific theory, and that's something to be discussed. But whether it's is or not, it may be true. Whether I like it or not, and I don't. What I've learned is that, again, the universe doesn't give a damn what I like. And so this may be true, but if this is true, when a universe pops into existence, the laws of physics pop into existence along with it. And so you got no space, no time, no particles, no radiation, no laws. To me, that's a pretty good approximation of nothing. Now, I want to end with another version of nothing. It was one that came to me from my late, very good friend, Christopher Hitchens, because I used to talk to him about science a lot. And when I told him about this, he said, you know what? Nothing is heading towards us as fast as can be. And I want to allude to the future. Alex talked about it a little bit, but the first person to realize the future was really miserable was of course, George Orwell, who said, to see what is in front of our eyes, one's nose requires a constant struggle. Okay? And this is clearly what he meant by it. What he meant is that if you put energy in empty space, constant energy, the universe is going to expand, and it's going to expand faster and faster and faster, and something that really hasn't been alluded to is eventually objects will be moving away faster than the speed of light. That's allowed in general relativity. We teach you that nothing can move faster than light, but we lie. Well, you have to be like a lawyer and parse it a little more carefully. Nothing can travel through space faster than light, but space can do whatever the hell it wants. And if empty space has energy, there are regions now, there are regions now moving away from us faster than light, and we can calculate that. In fact, we can calculate the distance away from us beyond which objects are now moving away faster than light. It's 18 billion light years, and the universe is 14 billion years old or so. So these effects are just beginning to be visible, and they're going to get worse. Because when objects are moving faster than light, we can't see them. The light can't make it back to us. They literally disappear in ways that I don't have time to discuss. But I've tried to use this, indeed, Alex, before Congress to say that we should measure things now while we have a chance. But the time frame of this happening is like, of what I'm going to talk about happening is 2 trillion years, and that's a lot longer than the long-term future for a congressperson, which is 2 years. So it doesn't work. Yeah, it never gets to us. Okay, but this means, and it's been alluded to, but in a much more dramatic way than I think it's been alluded to, the rest of the universe really disappears. And this means, in the far future, as was pointed out, I find it quite poetic. I said that a single human lifetime ago, we thought the universe was static and eternal. What I didn't say was that Hubble also was one of the people who discovered there was more than one galaxy. In 1925, the picture of the universe was that it was static, eternal, and the entire universe consisted of a single galaxy, our Milky Way galaxy. In 88 years, a single human lifetime, we've discovered 100 billion of them. That's why we're like the early map makers, just beginning to understand the universe on larger scales. It's not surprising that we're surprised all the time. But in the far future, it's very poetic. There'll still be stars around in 2 trillion years. There'll still be main sequence stars. And astronomers on those main sequence stars will evolve because there'll be carbon, and they'll evolve, and they'll discover the laws of physics, of quantum mechanics, of relativity. They'll build telescopes, and they'll look out, and what will they see? Nothing outside their galaxy. The universe that they believe they'll live in will be the universe we thought we lived in 100 years ago, with a single galaxy, and all evidence of the Big Bang will have disappeared. But after that happens, these stars will burn out, and the universe will become cold and dark and empty, as Alex said. So in that case, as Christopher put it, the simple answer to the question, why is there something rather than nothing, is just wait, there won't be for long. And I think that's the most important answer because it demonstrates our incredible cosmic arrogance. Many people think we're the pinnacle of evolution, but it's not as if evolution had some purpose to get to us and it stopped. Okay? And many people think the universe that we live in is the universe is the way it always was and always will be. It's not. It's going to be quite different. And we won't be around, and there'll be nothing around in the far future. So, to conclude, science has demonstrated that a universe from nothing is not only plausible, I would argue, but likely. And what's really important is that what we mean by something and nothing has completely changed from the time the classical philosophers and theologians first raised the issue thousands of years ago. That upsets some people when I say that science has changed the meaning of things. It came out of it. But it's actually called learning. Okay? We should celebrate it. And really, the important thing is that I want to point out is why is there something rather than nothing is not the important question. In fact, it's not even a reasonable question. Because why is there something rather than nothing assumes purpose. Whenever you ask a why question, it assumes purpose. In fact, why questions are fundamentally meaningless. Whenever we ask why, we really mean how. And anyone here who's a parent knows this. When your kids ask why, the only answer inevitably is because go to bed. Okay? What really is the important question is how. How did the universe evolve, and how can we find out? And that's what we're celebrating here today. And the amazing discoveries we've heard talked about are continuing, and the surprises that are going to happen, what we now know will pale in comparison to what the young people here will discover, as some of them, I hope, become scientists. So, to really conclude, I've told you two things. First, you are much more insignificant than you ever imagined. And second, the future is miserable. Okay? But you should be happy. Because, you know, we may live in a universe without purpose, but what does that do? That means the purpose in our lives are the purpose we create. And we should consider ourselves fortunate to have evolved in this place in the middle of nowhere and evolved a consciousness where we can understand the universe from the earliest moments of the Big Bang to the far future, sitting here in this remote place in the middle of nowhere. And so instead of being depressed, you should enjoy your brief moment in the sun. Thank you very much.
Thank you. Thank you, Professor Krauss. That was the best talk I've heard about nothing ever. At this time, I'd like to bring the panelists up for the question and answer period. And in a couple minutes, we'll get started with the Q&A session. Please pass your questions to the ushers as they come around. Great job.
That worked. I was able to build on what they said, so I felt good about it.
Yeah, that's really good. That's good.
Okay, good, thanks.
Yep. You got everything you need?
Yeah, I'm just going to put all this stuff away while I can. Yeah, no, in fact, I mentioned your name. I didn't make you happy? How can I not make you happy? Okay, I know, but it wasn't about you, yeah.
I don't worry about how you feel.
Yeah, no, I know. I know it's safe to say that you're good.
Hello, excuse me.
Yeah?
I really enjoyed your
I
talk.
think we got to do a panel, but I'll sign it.
Could you sign it?
Will you be here after? Okay, I'll quickly sign it.
Okay,
But-
thanks. Thank you.
Thank you. We're going to do the talk and then I'll sign it.
Okay,
Thank you. Okay,
thank you.
take care. I thought I'd thank you. Your audiovisual was perfect. If you want
I'll go ahead and get your power supply while then.
I think one of them.
step inside when he comes up here. I can help him get in.
He's coming.
Okay.
He's already on.
That way we can get started.
Okay. I'll get the crowd settled down.
Yeah, I mean, you can have him start the step.
It doesn't take you guys long to get one person ready. Okay, folks, we're going to get started in just about a minute here, so if you could find a seat, pass your questions to the ushers, and we'll bring them up front for us. Thanks.
Okay, we'll begin the Q&A session now with questions from the panel, and we'll start with Professor Filipenko.
So, thank you, Lawrence, for that very interesting talk. I wanted to clarify one issue, though. There are many issues, but one can imagine a universe spontaneously forming out of nothing as a result of quantum fluctuations, essentially, and then inflation making it grow, and it has essentially zero energy. But does it presuppose an existing set of laws of physics?
Well, it's a good question. We were talking about it before this began, but what I wanted to point out, the answer is yes and no. because
the answer is yes.
It could be that all possible laws occur. It could be that all possible combinations of laws, multiverse doesn't have to be finite. It could be that every possibility that can happen happens, and therefore every possible set of laws of physics may exist. And that's the same, it seems to me, as having no laws. And basically, it's saying that there's no selection effect. It's just anything that can happen happens. But it could be, and in fact, in the case of string theory, there is some underlying law. And in fact, you didn't say it explicitly, but I'll say it. I assume quantum mechanics there. In order to have quantum fluctuations, one has to assume quantum mechanics. I don't know how to, I can only work with what I have as a physicist. There could, as far as I know, it's possible that quantum mechanics itself may not be universal. We don't have a fundamental law of physics. So the answer is, of course, one doesn't know. And not knowing is a wonderful thing. And so there may be a unique set of underlying laws in an 11-dimensional universe. There may be every possible set of laws in the universe in this multiverse that can happen. And my point is, therefore, that it's not as if you need. If we ask what people really mean when they ask, what's the miracle of existence? Most of the time they say, how can you get the stuff we have unless someone said, let there be whatever? And the point is, it's not a miracle to have stuff where there was no stuff. That's no miracle. It's not a miracle to have a universe where there was no universe. That's not a miracle. And you don't have to have a uniquely set of prescribed laws of physics for our universe to arise. Indeed, there may be some underlying law of physics in the universe, and I don't know the answer. But that doesn't, to me, the important question is, how did our universe get here? And maybe I push this question, why is there something rather than nothing, back to the multiverse. I don't give a damn. It's not the thing that interests me. The interesting thing that interests me is, how did our universe get here? But it's an important question.
But even the multiverse, its existence is difficult to comprehend unless there's some underlying set of laws that allows it to.
But difficult to comprehend is different than existence. That's what's wonderful about physics, is that things that were difficult to comprehend happen. And we've been able to comprehend them. There may be ultimately things we'll never comprehend. I'm one of the people, I don't think we'll ever have a theory of everything. I would be amazed if we did. And I think that's the wonder and beauty of science. The mystery is what makes life worth living. And so, absolutely, I can't comprehend the words you're using. I can't comprehend mathematically, or because I don't. If I could, I'd write it down in a physics paper. And so you're absolutely right. These are issues we don't understand, but they don't take away from the remarkable fact that it used to be that life was a miracle and had to demonstrate something beyond the laws of nature. Happily, Darwin got rid of that. And I would argue that physics is getting closer to the point of saying, at least to understand how our universe got into existence, we don't have to posit anything supernatural.
I'm ready.
Frank?
Lawrence.
Well, go ahead.
Okay, Lawrence, first of all, stellar performance. I'm sure the audience appreciated it. And for these...
Anyway, okay, thank you.
And since you're such a great supporter of the string theory community, I want to thank you for your comments.
I like to give you free advertising wherever I can.
Thank you very much. But my serious question is the following. You might be surprised, at least in my own personal views of physics, that I find a lot of resonance with what you say. And in particular, the whole question about whether the laws of physics themselves actually had some sort of natural selection to act upon them. Would you be surprised if I told you that I, in fact, accept that and have some minor evidence that that is true?
Well, I wouldn't be surprised. First of all, I don't think you should accept anything. That's really a key point. So you shouldn't believe anything.
Well, when I say accept, I mean provide my own internal proof.
Okay. I mean, if you could see evidence, then that's a good bit. There's lots of indirect evidence, and I happen to think the phenomenon of inflation is the best motivated evidence that there might be a multiverse. It's my opinion. But no, I wouldn't be surprised that if you agreed, because I've known you for a long time, and you're a sensible guy.
That sounds like a cop-out to me.
So when you're saying evidence, do you mean a prediction that we can test experimentally?
No, I do not.
You want to give it? I mean, everyone's wondering. So why don't you give it?
Well, actually, some of the people in this auditorium have actually heard a talk. Lawrence, I've been mucking around down in the mathematics of supersymmetry, and we have found these weird, and some people say unimportant, but evidence of what looks like error correcting codes. There's only one place in nature, in the observed world that I know, where error correcting codes occur, and that's in natural selection. And it's even not completely clear there, but there are, as you know, geneticists who make that argument.
I mean, it's fascinating. I'm skeptical, but it's it's great. I think and it'll be amazing. I think what's amazing, and what I try to illustrate, is that we can even ask these questions. We could have had a symposium 30 years ago, a Nobel symposium, and we could have asked the questions, but we wouldn't have had any sensible. I mean, I'm not sure you'll argue that my answer is sensible, but we know so much more that we've gotten to the point where these questions are even discussed among scientists, which I find fascinating.
I think a lot of the issue that Alex was raising and many people raise in this connection is, what exactly do you mean by nothing?
Well, I thought I made it clear.
No, it wasn't obviously not entirely clear. As you know, almost exactly 30 years ago, in fact, I made a proposal very much along the lines that you discussed here in Scientific American, with a rather precise, however, formulation of what nothing means. What I took as nothing is the idea that the universe would begin in a very, very symmetrical state with no matter and much more symmetry. The symmetries that are broken in our world would be restored. We know many of them are restored, so we could assume that there was a much more symmetrical state early on with, for instance, equal amounts of matter and antimatter. And then I think it was already plausible then, and it's become, as you mentioned, much more plausible now, that the laws we know operating on such a state could lead to something very much like our universe. But I wouldn't overstate how that means you're getting a universe from nothing. You're getting a universe from a framework of an assumption about what the initial state is and what the laws are. And both of those are certainly still up for grabs to a large extent, especially the assumption about what the initial state is, or even whether we should assume an initial state. For instance, one can sensibly speculate about whether that's the right formulation at all. Maybe the right formulation that would be more symmetrical would be to say something about the final state.
Yeah, no,
I mean, cosmology, as you know, is a subject that's changed a lot. You emphasize that, in fact. And I don't think it's over yet.
Well,
even at a very fundamental level.
Well, I think obviously I resonate with a lot of what you said, and I agree that one should be careful, as you should have been careful when you wrote the Scientific American article and and said, why is there something rather than nothing? Because nothing is unstable.
That's
right.
That's
and so,
exactly what I said. Yeah.
And so we all use these terms, and what we mean, I think, look, one can have a huge philosophical discussion about the nature of nothing. I think it's largely a waste of time myself. But what we operationally mean is that you might say nothing is non-existence. And the question is, how could you get something that exists now from something that didn't exist before? That's the weird thing. Now, whether there was absolutely nothing else is an interesting question, but it's not the question I think that one's addressing. How can you get something that exists when it didn't exist? And actually, that's no surprise. People seem to find it a surprise. You know, look at the light from the photons are coming from that light. Well, they were emitted spontaneously by electrons that jumped between levels in atoms. Did the photons exist before the electrons emitted them? Absolutely not. So they're photons that came into existence. It doesn't bother anybody. Somehow it bothers people when we talk about a universe. So you're absolutely right. One has to be careful. No. But I tried. No space is one version of nothing, but no particles, as you pointed out, is one version of nothing, but no space is a much more interesting version of nothing. No space and no time, and pointing out that even a space can come into existence when it wasn't is a fascinating thing to talk about, and maybe.
But I think you're overstating how much that can be done. You need something. You need a space out of which another. You can have more space arising out of some space.
No, I think you're. No. Hold on a second.
It's very.
We agree that a space-time which didn't exist, a four-dimensional closed universe, could come into existence that wasn't into existence before. You will agree with that
But it doesn't start from nothing. It starts from a special initial.
But it doesn't start from a universe that existed before, because that universe wasn't there.
Well,
that's my
point. What you mean
point.
by a universe.
Well, the rest is semantics.
By nothing. No, it doesn't. It's. Well.
No, I mean, I think it's a remarkable thing that a universe can have zero. Well, you're not the only one who can interrupt, Frank, but it's a remarkable thing that a universe can have zero total energy and come into existence
no question. No question.
That's all I wanted to point out.
That when Einstein first learned about that, he almost got himself run over by stopping in the middle of the street in Princeton.
Yeah. No, and so I think ultimately we're in a
striking observation. There's no question.
Yeah.
But I think the thing that confuses and upsets some people, and well, in fact, I know it does, and
at least
not
one
me.
person.
It doesn't bother me. I don't care.
Oh, okay.
Except because of my sympathy for other people.
For humans.
But when you say nothing,
you said
it. That's you're threading your title. It means something to. It means different things to different people.
That's why I tried to find
it. When I
said
nothing, I tried to be careful about what I meant by nothing.
So did I.
Well,
I defined three different versions of it anyway.
I think once you start talking about the laws being random or no laws at all, you could really start from nothing at all. I think that's going too far. I think that it's really within a specific framework that you can discuss these questions. And you definitely invoked quantum mechanics, you invoked relativity, you invoked a lot.
Absolutely. I gave an example by which the universe could come into existence, but I made a key point that we don't know.
Lawrence, what do you mean by exist?
Well, that's a good question. It means having a panel discussion. Well, as a physicist, what existence means to me is that I can measure it. Or not that I can measure, that Tara can measure it.
And
or
that's fine.
Sam, someone else.
That's fine, but that does not exhaust the meaning of exist.
You're right, but it's all that I care about.
Okay.
Okay?
It's fine.
Okay, I mean, seriously, it's maybe my own limitation. Yeah. But if I can measure it, then as a scientist, if I can't measure it even in principle, obviously we talk about we've all created, the theorists on the panel, things we can't measure. But in principle, we can imagine them being measured. And as a scientist, if it's not related to that, it's just not science.
Right. So I would like to sort of tie that with what Frank was just saying. And that is, 30 years ago, you couldn't have this discussion. And 30 more years, you're going to have a really different discussion. I mean, the fact is, we're putting in a lot of scientific cultural prejudice into our models. And it is true, you can make up a model in which you get the universe we're living in today from a place that had no space and time and no particles and energy or something. That's perfectly a reasonable prescription you can kind of, I've actually assigned it as a homework problem and have my students choose the coefficient of the area functions to get the universe of their design. But it's much more difficult to be arguing about how to remove the context and how to do that.
Yes.
And, so this is where I have to voice my...
What do you mean how to remove the context?
Well, so one of the contexts that both of you talked about are the multiverses and the anthropic principle. And those are arguments about what's going on, but I can give you examples of universes that are much more probable than the one we live in, and examples of universes infinitely more probable than we live in.
Yeah.
And therefore,
it'd be great
even though rare things happen, we shouldn't have happened, right?
No, actually, that's the important thing. If it were really physics, it would be great. And one of my problems with I've worried about multiverses is that if we had a theory that allowed us to calculate the probability distribution over universes, well, that would require having a theory of the multiverse, which we don't have. Anyone who talks about probability distribution doesn't know what they're talking about because we don't have a theory yet. We can guess the probability.
Right, but if you're going to do the anthropic principle, you're immediately putting in probability distributions.
Well, you're assuming a selection effect, but you're assuming the probability distribution, but you don't. That's the problem with the anthropic principle, is it's always based on ignorance. Because if you really had a theory, you wouldn't have to use the anthropic principle anymore. You just calculate.
Right.
Lawrence, can I ask a really dumb question?
Yeah, I'm biting my tongue, but go ahead, yes.
You agree that space and time come into existence, yes?
Probably. I wouldn't
It's happening right now in this room.
No. I mean,
it's a serious question.
As you're well aware, there are models of bouncing universes that I find particularly ugly that go through something at which you have to do Planck scale physics. But you could have imagined an eternal universe that bounces. It doesn't obviate anything that I talked about.
But my point is, you talked about the dark matter particle going through the universe. In this space, it's expanding, right? And time is growing, right?
What? Where? The space between you and me isn't expanding.
Between my hands,
gravitation.
between us and the audience, right? It's just that gravitationally we got corrections going on.
Yeah, well,
but
it's
the
not
fact
expanding.
is, space is being created all the time, right?
Yeah, so?
So that was the question, right?
But if I could get back to my question, the point's much simpler. How do you have dynamics without time?
That's a wonderful question. I wish I had the answer. But the point is that when people talk about, in fact, one of the arguments, look, I've just come from Australia where I was having this debate with a Christian apologist. And the argument given of cause and effect, that there had to be some purpose because there has to be, the cause and there has to be universal, the first mover, all the rest of the stuff. The point is, you're absolutely right. If time comes into existence at the same time as space, then the question of what happened before is not a good question.
It's not a scientific question.
It's not a scientific question. But I'm not sure it's not a scientific question. It's not a question we can answer yet because we don't have an understanding of that theory and how time can exist. I don't think you will agree with me that there's a vast difference between things we don't understand and things that are not understandable.
Oh, absolutely.
And so it's absolutely true that I can't, as a physicist now, adequately discuss what I mean by universes without time. But that doesn't mean that someday one of the young people sitting here won't.
No, but I'm just saying that's an obvious hole in the argument.
There's a what? That's a what?
That is, to me, the most obvious hole in the argument. I don't know how to talk about dynamics without time.
Well, you can imagine, you can imagine, you can imagine a super space, and I wasn't going to say superstring, argument where you have a Hamiltonian and things look like they're static, but locally they're dynamics when you take part of the system. You know how to do all that.
Yeah, but then you have a pre-existing space in which there are laws of physics.
Not space.
And you haven't.
You don't our
space. But you have a pre-existing entity of some sort.
I don't care if there's a pre-existing entity. Our universe did not exist. It came into existence. That's the thing I wanted to discuss. And I don't see why people are worried about stuff we can't discuss. We can discuss possibly how our universe came into existence. Isn't that good enough to be celebrating on a nice afternoon in Minnesota?
I like it, but I want to know what happened beforehand.
Well, I would too, but I don't know.
I think we're all happy to celebrate the idea that we've progressed enormously in recent decades, and our understanding has pushed back the frontiers of what needs to be assumed as unexplained within our description of the universe. But I think it's far from the case that we've pushed it all the way back to nothing.
Well, I think we're in agreement. Because the point, and if you read and if you listen to carefully what I said and what I write, I never say we've pushed our understanding back to nothing. We've made certain postulates plausible, and that is fascinating. Darwin did not understand DNA when or the mechanisms of genetic mutation when he developed natural selection. What he showed it was eminently plausible based on the fossil record and what he knew that all the diversity of life came from a single life form. We now know much more, and what's great. I mean, and what I really want to do, and I want to emphasize, is not overstate what we know, but the very fact that we can begin to address these questions should get people interested in thinking about them as scientists.
Maybe a position that I'm very comfortable with, and have been for a long time, is that the ultimate laws that govern the universe, including both the laws and the initial conditions, or whatever substitutes for initial conditions in a final formulation, will turn out to be simple and beautiful. But it won't be 0 equals 0. It'll be something richer than that.
Well, that's nice, but that's much more speculative than anything I said. It's a nice idea, but
no, it's not.
We don't know it'll be simple and beautiful. I mean, it's nice. I'm glad it makes you happy. But,
I think it's what you're groping for.
But what's actually what's equally plausible, and I thought you were going to say, is that there may be no such thing as initial conditions. Initial conditions may be inseparable from final conditions, and their very question itself may be a bad question, and that's great. Yeah. That's great, and science will do, and that may change the picture. Yeah.
Well, but we don't know yet.
We don't know yet. And let's celebrate.
And we're pushing things. We're pushing.
Well, I'm pushing you.
But we're not. What's that? We're not pushing you. Okay, we'll try to pull you in.
I want to take a question from the audience and contextualize it a little bit. We've heard some talk about string theory not being physics because it's not testable.
I didn't say that.
Well, no, you would never say that. No, Jim's your friend. Is the multiverse theory physics? What this person is asking is, can we design or conceive of an experiment or set of experiments to explore the concept of the multiverse?
That's a really good question. Are we just talking metaphysics or is it physics? Is the multiverse physics? Because in principle, although it's possible in certain multiverse theories that universes can collide and then you'd know about it before you ended existence. But it could be that, and it's quite likely that if we're part of multiverse, that we'll never have direct causal information about the rest. But I think it can be science in the following sense that atoms were science before we knew about them. Namely, before we could measure them directly. One could imagine that we did have a very good theory that explained why there are 3 generations of elementary particles, why the proton is 2,000 times heavier than the electron, et cetera, et cetera, et cetera, why gravity is much weaker than the other force. And it could be a corollary of that theory that, in fact, we can actually predict that inflation must have happened, for example. And then we can make 50 predictions we should compare with experiments. But one of the inevitable logical consequences of that theory is that there's a multiverse. So we can probe 49 aspects of that theory and test them, and then we're willing to say the one equally logical consequence that can't be removed also must exist. So I think that's science.
I agree very strongly with that. In fact, I think we have an extremely useful and profound example of a theory that's very rich in consequences that can't be verified, and that's quantum mechanics. Quantum mechanics works on wave functions that have much more information in them than we can extract even in principle. So.
Yeah. Okay, we're in agreement.
Let me put forward one final question from the audience because I thought of it too during your talk. This idea that during the inflationary period we had sort of a closed universe, but it inflated so fast that what we measure appears to be flat. And the questioner wants to know, is our determination of the flatness due to our measurements, which you showed, it's really closed, but our measurements make us think it's flat because it inflated so fast?
It's obviously a good question. What we need to say, and we often need to be more precise, and me too, and we tend to say things. What we mean is that the measurable, observable universe is indistinguishable from a flat universe. But but the definition of universe has changed, of course. The universe, what we mean by universe is now that which we are in causal contact with, or ever could be in causal contact with, or ever will be in causal contact with in the future. And that's not everything. And so if that picture I gave, which is one version, which is that a closed universe is created, if that's true, then on sufficiently large scales, that closed space-time is curved. But inflation generically, although not universally, but generically produces so much expansion that the difference between omega 1 is in the 50th decimal place or something. So if we waited in a universe that lasts forever, if you waited long enough, you might see some evidence for that, except in a universe that happens to be dominated by vacuum energy, all that information will never be recovered because the rest of the universe will disappear.
Okay, we will close now and reconvene at 3 o'clock for Father Coyne's talk.
Okay, folks, we're going to get started now with the next lecture. It's my pleasure to introduce my colleague, Professor of Chemistry, Steve Miller, to introduce Alex Filippenko.
First of all, I'd like to apologize. I'm not going to have any exploding rocket sleds. So, thanks, Josh. If you, like me, are a fan of the PBS program Nova, you might well recognize Dr. Alex Filippenko, who has been a contributor to that show in recent years. I remember one episode in particular in which he was explaining Doppler shifts using the example of a car horn as the car drove down a highway. And as the car passes a stationary observer, the apparent pitch of the horn changes. I remember this instance not for the lesson in Doppler shifts, but because of the two questions going through my head at the time. What kind of astrophysicist gets to drive a classic Ford Mustang down the highway for a TV show? And how can I get that job? It turns out that the answers to those questions are respectively Alex Filippenko and I can't. Dr. Filipenko earned a Bachelor of Arts degree in physics from the University of California, Santa Barbara in 1979. And after that, he entered the PhD program in astronomy at the California Institute of Technology, where he graduated in 1984. He then accepted a Miller Fellowship to the University of California at Berkeley. And after the term of that fellowship, he accepted a full-time faculty position at Berkeley. And he has been there ever since. And he is now the Richard and Rhoda Goldman Distinguished Professor in the Physical Sciences there. He has done quite well in the intervening period. He was awarded a Guggenheim Fellowship in 2000. He shared the Gruber Cosmology Prize in 2007 and was elected to the National Academy of Sciences in 2009 among his many accolades. He's also one of the most prolific and widely cited astronomers in the world, having already published more than 700 publications. Dr. Filipenko's research largely focuses on identifying and studying supernovae, black holes, and other related objects or events. His group developed and operates the robotic Katzmann Automatic Imaging Telescope, or CATE, on the slide there, which has contributed to their discovery and characterization of more than 300 supernovae since it went into operation. The resulting data have contributed significantly to our understanding of the ways in which stars die. His group has also worked to identify possible black holes and study their relationships to other objects in the sky, such as galactic nuclei and quasars. But Dr. Filipenko is probably best known for his contributions to the work which will be the basis of his talk here today. In the mid-1990s, he was a member of both the Supernova Cosmology Project and the High-Z Supernova Search Team. These groups used observed redshifts in distant supernovae to demonstrate that the universe not only continues to expand, but does so at an ever-increasing rate. This discovery was hailed by Science magazine as the science breakthrough of 1998. It has since given rise to the idea of dark energy and resulted in the 2011 Nobel Prize in Physics being awarded to the heads of the two independent teams. Here's this picture. As impressive as his body of work as a researcher has been, a second talent contributes to Dr. Filipenko driving a classic convertible for a TV show while many others sit at home and watch. He is widely regarded as a great speaker, teacher, and ambassador of science. Among his many teaching accolades, he was named the Carnegie Foundation's 2006 U.S. Professor of the Year, and he has been voted by the UC Berkeley student body as their best professor a record 9 times. And remember, he teaches physics. It is ultimately his place at the forefront of modern astronomy and his ability to communicate its ideas clearly to colleagues and lay audiences alike that make him a natural contributor to Nobel Conference 49. And so please join me in welcoming Dr. Alex Filipenko.
There we go. Well, thank you very much, Steve, for that wonderful introduction. And I thank you all for being here. Wow, a full house. It's actually great that Gustavus Adolphus College is not shut down today, as is our federal government. I was a little bit worried there, yeah. So you all know where to be, here to listen to all these wonderful presentations at the forefront of science. As Steve mentioned, the 2011 Nobel Prize in Physics was awarded for the discovery of the accelerating expansion of the universe. And it was awarded to the leaders of the two teams. Saul Perlmutter, in the middle there, led the Supernova Cosmology Project, and Brian Schmidt, at right, led the High Redshift Supernova Search Team. It was also awarded to Adam Rees, on the left there, a member of Schmidt's team. He was my postdoctoral scholar at Berkeley in the mid to late 1990s when we did the research leading to this discovery. He was charged with analyzing the data. He was the first on the Schmidt team to realize what the data were trying to tell us, and I think it's appropriate that he received a share of the prize as well. I was the only person to have been at one time or another associated with both teams, and if you get me sufficiently drunk, I'll tell you the story behind that. It's unfortunate that there's a tradition among the Nobel Prizes in all fields other than the Peace Prize. They can be awarded to, at most, 3 individuals. And there were 48 others on the 2 teams that contributed to this discovery, and additional astronomers who did groundbreaking work in preparation for this discovery. And, without the hard work of all these other people, these 3 gentlemen wouldn't have been so recognized. My colleague at Harvard, Bob Kirshner, likes to quip, "It's not every day that you don't win a Nobel Prize." Anyway, these 3 gentlemen understood that without the rest of us working hard in the trenches, they wouldn't have been recognized in this way, and so they spent a good fraction of their prize money flying the rest of us out to Stockholm in December of 2011 to participate in Nobel Week. A nonstop set of parties and celebrations, receptions, all in the name of science. It was like the Swedish Super Bowl, actually, but for science. And I'm told that it was all televised, and in particular, the Swedes loved to observe the poor manners, primarily of Americans, at the Nobel banquet. So a topic of much discussion. Anyway, there's the Supernova Cosmology Project led by Saul. At the time, the High Z team, with which I was more associated, was having their team lunch, and I couldn't clone myself, and so I couldn't be in this photograph. But that's one team, and then the high redshift search is shown here, right after the awarding of the Nobel Prize to Schmidt and Rees on this team. And the rest of us like to say that we got to participate in nearly everything, all the parties, all the receptions, except for the handshake from the King of Sweden, the gold medal, and a share of $1.5 million. But that's the way it goes. All right, well, my talk today will be on cosmology, that subset of astronomy that deals with the structure and evolution of the universe as a whole. We're interested in some of the grandest questions. How big is the universe? Is it infinite, or does it somehow wrap around itself? What is its shape overall? What is its age? Is it infinite? Is it finite? This is a big time story. You see that? Big time story. When did the universe begin? Well, we now know that it began 13.8 billion years ago. A very long time indeed, but not infinitely long. And that's an amazing discovery, worthy of the cover of Time magazine. And you know that these national magazines want to educate the public, of course, but they also want to make money. And they won't choose a cover story that they think will not sell. But astronomy, and in particular cosmology, they sell. People are interested in this stuff. Cosmologists are also interested in the fate of the universe. Will it expand forever, or will it implode in on itself? This, too, was a big-time story, how the universe will end. And back in 2001, when this cover story was written, we thought we knew how the universe would end, and so there's no question mark there. Now, a dozen years later, we've conducted more research, and we're not so sure how it will end. But I will tell you how we think it will probably end, the betting person, all right? How to lay your odds. Cosmologists are also interested in the fundamental building blocks of the universe. Those are galaxies, gigantic, gravitationally bound collections of tens or hundreds of billions of stars. Now, our Milky Way galaxy would look like this if we could see it from the outside. This is not a picture of our Milky Way. If anyone has such a picture of the Milky Way, please see me afterwards. I'd like to purchase usage rights from you, okay? This is seen from up above. But it's about 100,000 light years from end to end, and light travels, 186,000 miles a second, 6 million miles per year, and it's 100,000 of those units across. So if you were on a planet orbiting a star here, and you sent a radio signal at the speed of light to an alien friend over there, saying, hey, let's go to the Nobel conference, the 49th one, that is. It would take 100,000 years for your signal to reach that friend, and another 100,000 years for the reply to come back saying, well, let's go to the 200,049th Nobel conference, okay? Round-trip conversation of 200,000 years, hardly a stimulating conversation. I'm sorry, this is the way the universe is built. I'm just the messenger here. It's built out of these gigantic galaxies. And there are lots of them. Here's one of my favorite photographs from the Hubble Space Telescope, the Hubble Ultra Deep Field. The telescope stared at just one tiny part of the sky for the equivalent of 2 weeks, collecting light, seeing ever fainter objects. And this is a tiny but representative fraction of the sky. Imagine a grain of sand held out at arm's length. Imagine how small that looks. That's about the size of this picture here. And everywhere it's filled with galaxies. I could spend my hour counting them. 1, 2, 3, 4, 5. That would be pretty boring for you. But hey, it's a rather cushy job. They pay us to sit around and count galaxies. What could get better than that? Anyway, we've taken a number of such photographs, and we can tell that this is representative. So, extrapolating over the whole sky, we can estimate that within the realm of today's great telescopes, there's something like 100 billion galaxies. And that's just in the parts of the universe that we can see. We now have very good reasons to believe that the universe extends far, far beyond the parts that we can see. And everywhere it is filled with these galaxies, the basic building blocks. How do they form? How do they evolve with time? These too are among the central questions of cosmology. So you can see what an amazing, vibrant, intellectually interesting field it is. And I feel very privileged to have been able to work in this field and contribute to the findings. Now, before I move on, let me point out that among the general public, present company excluded because you're at this conference, you're interested, you're somewhat knowledgeable. But among the general public, there's considerable confusion between cosmology, the study of the structure and evolution of the universe as a whole, and cosmetology, the study of hairdos and facials. Now, I admit they sound similar, as do astronomy and astrology, by the way. But they are different. They're spelled differently. In fact, if you write them down, you will find out that cosmetology is simply cosmology with an extra ET in it, like the extraterrestrial. I don't know the cosmic significance of that, but nevertheless, that's how they differ, and they mean rather different things. Now, you might say, surely people don't have this confusion. Show me the evidence. Well, I'm a scientist. I will show you the evidence. Here's a copy of an ad that a colleague of mine placed in my mailbox some time ago. Make cosmology your career. Training and supervision in hairstyling, blow drying, permanent waves, coloring and frosting. You laugh, but these are very important topics, okay? Scalp treatments, body and skin care, style cuts, basic cuts. For further information and interviews, call that number. Now, classes started back in March, so you missed the spring quarter. But I'm sure this will be offered at your local college or university in the next quarter or semester. So if you want to do, as I and many of my colleagues have done, and get to the cutting edge of this field, you need to take a course like this. Well, these guys need a course not only on their own profession, but a course on spelling and proofreading, because in addition to feather here, you see hair slying. Oops, hair slying. See that? And coloring. Well, that's the British spelling, and my own thesis advisor was British, so I'll allow that one. Anyway, maybe their spell checker wasn't working or something, but they don't even know their own field. Actually, my father-in-law says, you know, Alex, the only real difference between your UC Berkeley course on cosmology and a course on cosmetology is that you don't give makeup exams. Oh my goodness. See, my students have to put up with me every other day. You willingly came here. Puns are a highly underappreciated form of humor, but both my father-in-law and I like puns quite a lot. All right, well, the story of cosmology, in a sense, starts with Vesto Slipher, the observational story of cosmology, an astronomer in Arizona who examined the light from galaxies before it was even fully understood that they were actually outside our Milky Way system. He passed the light of galaxies through a prism, producing a rainbow, a spectrum. From the spectrum, a scientist can tell all kinds of interesting things about the object he or she is studying. We can tell the temperature of the gases, the pressure of the gases, the chemical composition. For example, this line is due to hydrogen. There's neutral sodium. There's singly ionized calcium, that pair of lines. A trained spectroscopist can recognize the fingerprints of different elements and their ionization stages. But we can also tell whether an object is moving toward us or away from us, and how fast. If it's moving toward us, the pattern of these lines produced by various elements remains the same, but shifted toward bluer colors, shorter wavelengths, higher frequencies. And if the object is moving away, then you get a redshift. So the audible version of this phenomenon is quite well known. You hear the siren going like that. And that's because as it's coming toward you, in between the emission of two consecutive wave crests, the siren has moved toward you, making the distance between the wave crests smaller, the wavelength shorter, the pitch higher. Conversely, when it's moving away, during the time between the emission of two wave crests, the object has moved away, thus stretching the wave, giving a lower pitch. Now, if you hear an ee-ah, it doesn't mean that the driver is drunk and can't make up his mind which way to go. It just means you don't have a constant pitch siren. But you can hear that it goes from high-pitched to low-pitched. Well, Slipher noticed that with few exceptions, other galaxies have redshifted spectra. But he couldn't do much else with this discovery because he didn't know the distances of the galaxies. Enter Edwin Hubble, after whom the Hubble Space Telescope is named. He measured the distances of relatively nearby galaxies using a technique I'll describe in a few minutes. And he found something very interesting. They're all moving away, other than those that are so close to us that they're gravitationally bound to us. Forget about them. So they're all moving away. But right now, at a given time, the more distant ones, which generally appear fainter and smaller in the sky, they're moving away faster. Okay? So there's a greater redshift, a greater recession velocity at greater distances. Now, Hubble resisted this interpretation for a while, but we now know that in the case of the galaxies, the redshift is caused by a stretching of space itself, not by the motion of particles through a pre-existing space. So in fact, it's not the classical Doppler effect. Basically, Earth and objects that are bound, that are solid, we're bound by electromagnetic forces, we're bound to the Earth by gravity. Anything that's bound to be strong doesn't expand. You may think you expand after a big lunch, but that's your fault, that's not the universe's fault. But the space away from strong gravitational fields does expand, and electromagnetic waves, light, expands with it. And so you can see that you start out with a short wavelength blue wave, and it gradually becomes longer. That's the cosmological redshift. It's an expansion of the universe. And there are ways we can now distinguish that from motion of objects through a pre-existing space. And it's definitely an expansion. So from our perspective in the Milky Way galaxy, a snapshot of the universe looks like this. All the galaxies are moving away, and the more distant ones are moving faster than the nearby ones. Now let me pause here for a second, because there's something kind of strange about this diagram as I've drawn it. What's peculiar about it? Yeah, a bunch of people said it. We're at the center. Why would that be? You know, do all these other galaxies not like us? Is it something we said, or do we smell? Are all these other galaxies lactose intolerant? Get it? Milky Way galaxy, lactose intolerant galaxies. When I talk about cosmology to my introductory astronomy class at Berkeley, I say, what is it? Are we from Stanford or something? Big rivalry, okay, academic and athletic. No, I mean, first of all, with due apologies to those of you who might be Stanford alumni, it's an outstanding institution, it really is. Just not quite as outstanding as Cal. Anyway, we don't think we're in any privileged position. We think that this is a property of a uniformly expanding universe. Let me show you this little demo, which I noticed was on the slide that started the presentation that Steve had. Here's a hypothetical one-dimensional expanding universe where the ping pong balls are the galaxies. They're gravitationally bound. They're not expanding. And the rubber is the space between them. So fix your attention on this ping pong ball. All the others are moving away. But the same could be said from the perspective of any other ping pong ball. And let this rubber be either infinite or wrapping around itself. The edges are irrelevant here. I'm not trying to fool you in any tricky way, all right? You get this apparent centrality in the universe without actually being the unique center. Notice also that the more distant ping pong balls move faster than the nearby ones because every little bit of space stretches. And the more space there is to begin with, the greater will be the stretching in a given amount of time. So this explains Hubble's relationship. It works not just in one-dimensional universes, works in three-dimensional universes. Here's an expanding loaf of raisin bread where the dough is uniformly filled with yeast. You let it bake for an hour, all the guys move away from each other. Again, imagine an infinite universe or one that wraps around itself. This one thinks that it's at the center, but all the others say that they're at the center as well. And in fact, there is no unique center, at least not in the dimensions that we can physically probe. There may be a center in a mathematically definable dimension, and I can discuss that later in the Q&A with, say, a balloon. Anyway, notice also that the more distant raisins move away faster than the nearby raisins. This one went from 5 centimeters to 10 centimeters. This one went from 10 to 20 in the same amount of time. That's because, again, every bit of space expands. The more there is to begin with, the greater will be the expansion factor. Okay, so that's the expanding universe. And with today's modern telescopes, we've measured pretty well the current rate of expansion. And you might think we're done. But we're not done, and this goes all the way back to Newton, who considered gravity. And here's an apple. You can't give a talk about gravity without using the proverbial Newtonian apple, so here it is. Boom. He supposedly watched it fall from a tree, and he wondered whether whatever it was that makes it fall is somehow related to what keeps the moon in its orbit. And Frank showed the interesting diagram from the Principia, imagining the cannonball fired at different speeds. Indeed, there is this deep connection, this law of universal attraction. So if we toss the apple up, the mutual gravitational attraction between the apple and the Earth slows it down. And in fact, it comes to a halt at the top and then comes back to my hand. So suppose you have a dense universe, a lot of matter per unit volume. Then every unit volume will be pulling on every other unit volume a lot, slowing down the universe quite quickly. In that case, the currently expanding universe would someday stop expanding and then collapse. It would implode on itself. So in this case, you could say Big Bang, Big Crunch. It starts with a Big Bang, ends with a big crunch, high densities, high temperatures again. Or you could say Big Bang gnab gib, which is Big Bang backwards, okay? So that's what kind of universe you would have if it were a dense universe. If you were lying on your back looking at the galaxies through a telescope, you would see them getting smaller and fainter, and you would say that's a well-behaved universe. And then you would notice something a little bit odd. They would get brighter and bigger again, and right around now you'd start getting a bit nervous, and then it'd be, goodbye, cruel world, and you would be crushed into oblivion, all right? So that's one possible fate of the universe. But there's another possibility. Suppose I had eaten my Wheaties this morning. In that case, I could heave this apple, forgetting about the technical difficulty of a ceiling here, I could heave it at a speed greater than or equal to Earth's escape speed, around 11 kilometers per second. And in that case, although it would be slowing down forever, it would never come back. It would either approach zero speed as time approaches infinity, or it would approach some constant positive speed as time approaches infinity. So that would be an apple that never comes back. In a low-density universe, all the galaxies are pulling on all the other galaxies, slowing down the expansion of the universe, but not enough to ever have it implode in upon itself. That would be an eternally expanding universe, and if you were watching galaxies on a dark Minnesotan night, you would see that they keep getting fainter and smaller, although at a progressively slower rate. So eternal expansion versus the gnab gib. Which one is it? We want to know. Doesn't matter that we'll not be around to see what will actually happen. We just want to know. That's what drives all scientists. How might we proceed to find out? Let's go back to the apple. Measure the speed of the apple at different stages of its path. See whether it's been slowing down a lot, in which case it'll stop and come back someday, or not slow down a lot, in which case it'll keep on going away from the Earth forever. Examine the past history of the motion of the apple to predict the future. So in a similar way, examine the past history of the expansion of the universe in order to determine the fate of the universe. Well, to do that, we need to know how far back in time we're looking. Here are galaxies that are far away, say 1 billion light years away, 4 billion light years away. Maybe that little blob there is 9 billion light years away. You're seeing them as they were 1, 4, 9 billion years ago, because it takes time for light to travel from there to here. In fact, fun fact to know and tell, light travels about a foot per nanosecond, a foot per billionth of a second. So I'm seeing Steve, not as he is right now, but as he was maybe 25 or 30 billionths of a second ago. He may not even exist anymore. Oh, he does. Good for him. He's still on this good earth. You see the sun as it was about 8 1/3 minutes ago, because that's how long it takes to traverse 93 million miles, okay, the light. You see the typical stars in the sky. The bright stars are some tens or hundreds of light years away. In a few cases, 1,000 light years. So you're seeing them as they were tens or hundreds or thousands of years ago. So if you look at galaxies that are 1, 4, 9 billion light years away, you're seeing them as they were 1, 4, 9 billion years ago. You're looking back in time. Telescopes allow us to look back in time. And encrypted in the light from those galaxies is information about how much the universe has expanded during the time that the light was traveling. That information is the redshift, okay? So if you know distances, hence look-back times, and you can measure redshifts, then in fact, you can reconstruct the past history of expansion of the universe. So how do we determine distances? For relatively nearby galaxies, it's pretty easy. This is the technique Hubble used. This is a Hubble Space Telescope picture. He didn't have those, but in such a picture, you can sometimes see individual stars. Let's call that one Chuck, just for kicks. And let's say we know through studies of Chuck that it's the same kind of star as Betelgeuse, the left shoulder of the great hunter Orion in the sky, okay? And this is a relatively nearby star. We know how distant it is. We can measure how bright it appears to be, and thus we can calculate the true power. If we now say, well, Chuck is the same type of star, and there are different kinds of stars, by the way, you can figure out how far away Chuck must be in order to look this faint. And if you do the same thing with other stars, Tara and Frank and Lawrence and others in this galaxy, and you get the same result each time, well, that builds confidence that your technique is correct. And in fact, Hubble used a type of star known as a Cepheid variable. Now, this is the same principle by which you judge the distance of an oncoming car at night. You've calibrated how bright the headlights are of a car of known distance, 6 feet away. You say, ooh, those are pretty bright. And then you look at dimmer headlights and you almost intuitively, almost instinctively calculate the distance of the car. And if you're not very good at doing this, then you shouldn't be driving at night, okay? You get a consistency check through the angular separation of the two headlights. That gives your brain a consistency check because the angular separation decreases with increasing distance. Well, cars, stars, it's the same idea. Find stars of known luminosity or power or oomph, measure how bright they appear to be, and thus determine their distance, and thus how far back in time you're looking. Now you might say, well, that works fine for nearby galaxies, but what about these galaxies here? You know, how do you know that that one's 4 billion light years away and not 5 or pi or something like that billion light years? All the stars are too faint to be seen individually, and they merge together. So it sounds like you're hosed if you want to look far enough back in time in order to really trace the expansion history of the universe. But you're not hosed. There is one type of star that's so brilliant that it can be seen at distances of billions of light years and separated from its neighbors. Anyone know what kind of a star that is? A supernova. Someone said a type 1a supernova. Ooh, boy, you know a lot. Okay, want to come give this talk? Anyway, so yes, a supernova, an exploding star. Now, very few stars explode at the end of their lives, but those that do can become millions or even several billion times as powerful as the sun. And here's one in a galaxy where I've sped things up a bit. It typically takes a few weeks to rise and many months to decline. At its brightest, that supernova is about as bright as the central few billion stars in this galaxy. They're really bright. If our sun were to do this, and it won't, don't worry, be happy, but if it were to do this, sunblock of 50 just wouldn't cut it, folks. You'd need sunblock or supernova block of a few billion to protect yourself. But that's not going to happen, all right? Okay. Well, you first have to find a whole bunch of relatively nearby supernovae in galaxies whose distances have been measured through observations of relatively normal stars in those galaxies, because it's the combination of known distance and measured brightness that gives you the luminosity or power of a supernova. But you've got to find a bunch of these things because there might be more than one way in which stars can explode. Indeed, there are several ways in which stars can explode. And even given a single physical mechanism, you have to measure whether there's a dispersion, a variation in the peak power. So you've got to first find a bunch of nearby ones. Now, this is a bit hard, actually, because in a typical galaxy, a star might explode only once every 30 or 40 years. So if I were a really cruel advisor, I would have each of my students staring through the eyepiece of a telescope at one and only one galaxy, preferably at night. You see more stars and galaxies at night than during the day. Until the student finds a supernova. And then we would let the student graduate and move on to greener pastures. Meanwhile, I will have had decades worth of slave labor from said student. Now, there are some crimes that are so egregious that even a tenured professor can and should get fired. I mean, we can't take advantage of students in this way. But we can improve the odds by observing lots of galaxies. So let's say there's one supernova per galaxy per century. Statistically, that's the same as one supernova per 100 galaxies per year. each of these 100 galaxies will produce a supernova sometime in the next century. Odds are that there will be one a year. Maybe some years there will be 0, some years there will be 2 or 3, but roughly one a year, okay? Or if you monitor 1,000 galaxies, there will be 10, all right? So that's getting to be pretty good. I could have my students scanning thousands of galaxies until they find several dozen supernovae. Then we let them graduate and move on to greener pastures. But this would be considered, you know, terrible punishment to the student as well, right? This would be an egregious crime, and I would probably get fired. Because, you know, students need to study and sleep, and most importantly, party, all right? Fortunately, with modern technology, we have a better technique. We attach digital cameras, like your little CCD camera, to the eyepiece end of a telescope, and we take photographs of thousands of galaxies throughout the sky, and we simply look for arrows. And where there's arrows, there are exploding stars. You see, it worked once, twice, 3 times, 4 times, 5 times. By rigorous mathematical induction, I conclude that this technique works every time. Well, obviously, it can't be quite that simple, otherwise we wouldn't give degrees for this kind of work. A number of teams, including my own, have developed largely robotic telescopes that do the work for us. And here's the telescope that my team runs at Lick Observatory, the Katzmann Automatic Imaging Telescope. It's been expertly programmed to look at over 1,000 galaxies a night, nearly 10,000 in a week. And it compares the new pictures with the old pictures, and it finds supernova candidates. Here's an example. Wei-Dong Lee, my close associate, expertly programmed it. Here's a before picture of a galaxy, and then here it is again. And there's something new. There's this arrow here. Well, the arrow was put in with Adobe Photoshop or something. The new thing is this little guy there. And that's a supernova candidate. It's not necessarily a supernova. It could be a cosmic ray, a charged particle that interacted with the detector in a way that looks like a star. Or it could be an asteroid flying through the field of view with Earth's name written on it. Astronomers will someday save humanity by finding the asteroids decades before they hit. And then physicists and engineers will figure out a way to deflect them. So you know, together we will save humanity. Anyway, one person's garbage is another person's gold. We don't care about the asteroids. We screen out most of the several dozen candidates that are found automatically by the system each night and focus on the 1 or 2 that appear interesting. And this is done by slaves, I mean undergraduate students who, through their superior eye-brain combination, examine the candidates at the end of each night and determine which ones are likely to be genuine supernovae and worthy of further consideration. And I'm very proud of my team. For about a decade, we actually found more nearby supernovae than all other teams in the world combined. And actually, Steve, our current count is closer to 1,000, exceeding 900. So you saw an old reference. I should update that. Let me know where you found the 300, okay? Because that sounds a little bit embarrassing compared to 900 or 1,000. Anyway, I'm very proud of my team. And this fellow at the left is kind of interesting. There he is. I like to say that he's the cosmetologist in our group, okay? Maybe he's trying to get a date or something, and then I realized I teach at Berkeley, and so this is not at all unusual. Every week I have a pizza lunch for my group. I bring them pizza, and they justify their existence for the past week. Anyway, through studies that we've been doing, and many other teams as well, and by the way, the studies with Kate did not contribute to the Nobel Prize winning work. Other studies had already calibrated supernovae pretty well before that, but we've been refining the technique since that time, and a number of groups have been working on this, okay? Nevertheless, we've contributed to this, and we and many others have found that when you pass the light of supernovae through a prism and produce a spectrum, you find that they come in 2 main types. There are now many other types, but they're called type 1 and type 2. Now, we could have called them Fred and Jean, but we call them type 1 and type 2. Astronomers are kind of boring people. Type 1s don't have any evidence of hydrogen in their spectrum. They have everything else: calcium, magnesium, iron, sulfur, silicon, oxygen, but no hydrogen. This is important. because hydrogen is by far the dominant element of the universe. By the way, these supernovae produce and disperse into the cosmos the heavy elements of which we are made. So the carbon in your cells, the oxygen that you breathe, the calcium in your bones, the iron in your red blood cells, all of these elements were generated in stars prior to and during their explosions and ejected into the cosmos, making them available as raw material for the formation of new stars, planets, and ultimately life. And this is what Sagan meant when he so eloquently said, "We are made of star stuff." He did not discover this, but he popularized the notion. Quite literally, the heavy elements in your bodies were created by stars many billions of years ago. So you are not just within the cosmos, but part of the cosmos in this very direct way. If that does not grab you, you were either brain dead or you were momentarily thinking about something else, like the government shutdown or how the football team did or something. I know it happens to me all the time, so let me not accuse you of being brain dead. But anyway, type 1s, no hydrogen. Type 2s, they do have hydrogen. Okay. The type 1s in particular have a subclass called type 1a, which is thought to come from a weird kind of a star, kind of like what our sun will turn into at the end of its life. It'll be what's called a white dwarf, made out of degenerate matter, not because it's morally reprehensible, but it's very, very dense, and this is the term that quantum physicists give to it. And if you're part of a binary system, which our sun is not, then the white dwarf can steal material from the other star, grow in mass, and become unstable at some point and explode. Or it can merge with another white dwarf to which it's gravitationally bound. And that gives rise to a type 1a supernova. They are very luminous. They're nearly all the same. There are some differences among them, and we had to generate ways to read the label on the light bulb, but I won't go into those details. All right. So because of the work of many, many people, by the late 1980s, early 1990s, it was already recognized that type 1a supernovae are excellent cosmic beacons with which to determine distances of galaxies and hence look-back times. So two teams set off to find distant examples of type 1a supernovae and to measure them. And a given supernova is used in two ways. Its apparent brightness is used to determine the distance and hence the look-back time of a galaxy, using the inverse square law of light, which I described before. The recession speed, or the redshift, due to the expansion of space, is measured from the spectrum. So the supernovae are critical for these two reasons: measuring distances, hence look-back times, and redshifts. And it's the relationship between look-back time and redshift that traces the expansion history of the universe. The teams found the supernovae using telescopes primarily in Chile, equipped with wide-angle cameras that could survey thousands of galaxies at a time. This is a picture, roughly the area of the full moon. Now, the full moon is not rectangular in shape, but this has about the same area. And nearly every little blob you see here is another galaxy, not a star in our own Milky Way galaxy. There are thousands of them. You know, with your naked eye, the sky is dominated by stars in our own galaxy. But when you take deep photographs with big telescopes, the sky is dominated by other galaxies, okay? So if you take a bunch of photographs of different parts of the sky like this, and then repeat the process 3 weeks later, some of those, roughly 100,000 galaxies, will have produced a type 1a supernova. They're pretty rare. They're once per galaxy per several centuries, actually. Nevertheless, with 100,000 galaxies, any sample examined 3 weeks apart will reveal a dozen or so of these things. You can do the math. So they're found by digital subtraction. Here's part of an image taken on the 7th of April, 1997, another one the 28th of April. You subtract the earlier one from the later one, you get a bunch of noise. That's okay. Every measurement process necessarily has some noise associated with it. But here, cleverly placed in the middle of the square, is something that looks like it might be real. And a Hubble picture of it a few weeks later reveals it as well, and it's marked with an arrow, so it's got to be a type 1a supernova, right? Well, it's not that simple. You have to get the spectrum, the fingerprint to be sure, and you need the spectrum in order to determine the redshift. And that was my main role on both teams. I'm a spectroscopist by training. I've studied supernovae since the mid-1980s, and I have access to the world's greatest optical telescopes, the twin 10-meter Keck telescopes in Hawaii. These are gigantic light buckets with which we can collect the data and disperse the light into a spectrum. These are amazing machines to use. 36 hexagonal segments structured in a honeycomb pattern, acting in unison like one mirror, but much, much cheaper to make. And this technique was invented by Jerry Nelson when he was at Berkeley. He's now at Santa Cruz. Here's Fred Chaffee, a former director of Keck, showing for perspective the size of the telescope. And he usually wasn't there when we were taking data. The extra light gathering power provided by his pupils is dwarfed by the glass here, so this is just a PR shot. Anyway, I would get spectra of the supernova candidates that my colleagues got, and they would look sometimes something like this. Here's a nearby type 1a, brightness versus wavelength, a lot of squiggles, and one at redshift 0.455, which means it's roughly 5 billion light years away, has the same squiggles. Some small differences due to noise and stuff, but no great differences. And when we got data like this, well then, I was a very happy camper. And now you see the real reason we build observatories in Hawaii. I find San Francisco Bay Area water to be too cold for swimming without a wetsuit. Well, here are 3 examples of type 1a spectroscopically confirmed supernovae, marked with arrows. And the punchline is they're faint. They're really, really faint. And you might say, well, big deal. They're in these scrawny, pathetic-looking, faint galaxies that are obviously far away. I mean, here, look, you can't even see the galaxy there. I mean, it's there, but you can see the supernova. So these are obviously very distant galaxies, so you expect the supernovae to be faint. That's true, but these were fainter than they have any right to be. They imply greater distances than could be accommodated in a well-behaved universe. Distances that were greater than expected based on their redshifts in any well-behaved universe. Let me give a simple example. Suppose I go back to the apple, and suppose I toss it, and I assume the universe is just 1 second old, okay? I can measure the distance of the apple from my hand after 1 second. That's some distance. But the apple has slowed down in its upward journey. If the mass of the Earth were less, then for the same toss, there would be less deceleration, and in 1 second, the apple would go farther. Now, I can't make the mass of the Earth less, but I can do the next best thing. I can toss the apple faster, and it's the same desired effect. It goes farther in 1 second. Now, suppose the Earth didn't exist at all, and you ignore Jupiter and the sun and all those other things. Would there be any reason for the apple to slow down? Hey, physics students, any reason for it to slow down at all? No, that's just Newton's first law of motion. It would keep on going in the same direction with a constant speed. So in 1 second, it would traverse an even bigger distance, right? But that's the biggest distance you can get under the influence of gravity or no gravity. What we found was that the supernovae, the galaxies in which they're located, the apples, so to speak, were at greater distances than you could have reached in the amount of available time. And we had to rule out other possibilities for what might be going on, like maybe there's fog in the way making the supernovae look too faint or something. But we ruled all that out. So the natural interpretation is that they're at a greater distance. To achieve that greater distance, what must you have? Acceleration. That's right. If I attach a rocket to this apple and it goes zoop, then in 1 second, it can cover a greater distance than that which is covered with no deceleration. Just no forces acting upon it. Now, you might be wondering, well, wait. Your argument depended on an assumed age of the universe. What if it were 2 seconds old? Then obviously the apple goes farther in 2 seconds. Good try if that's what you were thinking, but the detailed argument is independent of the assumed age of the universe. Really, the measured distances were greater than expected given the redshifts in any decelerating or constant expansion universe. And so the implication was acceleration. And I was privileged to be able to announce this result at a meeting in the Los Angeles area in late February of '98. The headline that came out was, "Astronomers see a cosmic anti-gravity force at work." We use this term anti-gravity hesitantly because people ask us, can we gather this stuff, whatever it is, and attach it to our cars and levitate over traffic jams? And the answer is no. It's either a property of space that cannot be harnessed, or there's so little of it that it'll never be harnessed with any, reasonable amount. Nevertheless, it has an anti-gravitating-like effect, all right, in that it accelerates the universe rather than decelerating the universe. A very strange thing. And no one would have paid attention had there not been two teams that came up with the same result at about the same time. This forced other physicists and astronomers to take the results seriously. The High-Z team submitted their paper in March of '98, and it was published in September of '98, and the Supernova Cosmology Project submitted in September of '98, and it was published in June of '99. And so because there were two teams that got the same result, people had to take notice. Maybe the technique is flawed. That's still a possibility. And so every scientific result has to be verified through independent techniques, for sure. But at least there were two teams using the same technique that got the same answer. That probably meant that neither one of them made some really stupid error like a programming error, 2 + 2 = 5, which is a huge embarrassment and causes you to lose your funding. Well, by the end of 1998, no one had found any obvious flaws in the methods by which the data were collected or analyzed or interpreted. So the editors of Science magazine proclaimed this to be the single most important discovery in all sciences in 1998. And the caricature of Einstein is surprised here. You might think it's because he's blowing multiple universes out of his pipe. Now, Lawrence might talk about this later, the fact that we think that there are multiple universes and they come from the pipes of famous theoretical physicists. Well, the first part of that statement might be right. Okay, there may well be multiple universes. I'm actually pretty convinced that there are, but I have no definitive evidence. No, he's surprised because this one universe is expanding faster and faster with time rather than more and more slowly, as a well-behaved universe would. He's doubly surprised because he has a sheaf of papers here where there's an equation. The Greek letter lambda equals 8 pi g, Newton's constant, times the density of the vacuum. Now you might say, whoa, the Nobel Conference organizers have sunk to new lows, inviting this bozo from Berkeley, who's talking about the density of the vacuum. You were taught on your mother's knee that the vacuum is sheer emptiness, nothing at all, zilch. How can it have a non-zero matter or energy per unit volume? Well, again, I'm just the messenger here. This was Einstein's idea. He was a lot smarter than I am. He came up with this possibility when, in 1917, shortly after developing the general theory of relativity, he realized that, the universe should be either collapsing in on itself because the gravitational force between galaxies should be causing them to implode on each other, or maybe the universe was started out in an expanding state, in which case it should keep on expanding. But there was no evidence for anything but a static universe. The sky didn't appear to be falling. There was no evidence for change. He and many others found a static universe to be aesthetically pleasing. So he introduced an idea, the cosmological constant, an effect of unknown physical origin, which acts in a direction opposite to that of gravity and has a magnitude exactly equal to that of the attractive gravity. That would prevent a collapsing universe. It's like this apple. It all goes back to the apple. If the net force is 0, the apple doesn't move, or at least it doesn't accelerate. If the net force is non-zero, then it accelerates. You know, George Lucas said, "May the force be with you." No, no, no. May the net force be with you. He has to go back to freshman physics, okay? The force may be with you, but if some other force is against you, then you're going to lose. May the net force be with you, okay? Here the net force would be 0. Einstein didn't like this because it appeared to be a mathematical fudge factor that did not make the equations mathematically wrong, but it made them look less aesthetically pleasing. There had to be this fine tuning between the size of the upward arrow and the downward arrow, for which there was no real physical reason. And there was certainly no experimental evidence in a laboratory for this effect. And this effect implies that the vacuum energy is non-zero and that it's repulsive. And many physicists found that to be a repugnant idea. So Einstein never liked the cosmological constant. And when Hubble, 12 years later, discovered that the universe isn't static after all, the whole physical and philosophical motivation for the cosmological constant vanished. Einstein renounced the idea, supposedly as having been the biggest blunder of his career. Because had he not introduced it, he would have predicted, as some theorists did do, that the universe is likely to be in a dynamic state, either collapsing or expanding. He could have been famous had he not introduced this idea. So here he is, sad that he ever introduced the idea. Now, I don't know that that's what he's thinking, but it could be what he's thinking. What have we done the better part of a century later? We've reincarnated the idea, not to have a static universe, but one which over the largest scales is accelerating, is expanding faster and faster with time. So here in this room, the down arrow dominates. Everywhere in our solar system, down. In our galaxy, down. In our local cluster, our local group of galaxies, down. But as you get to sufficiently large scales of order 100 million light years, the up arrow dominates and the universe expands faster and faster with time. And if Einstein were around now, he would see that maybe his biggest blunder was actually his greatest triumph, the idea of such an effect. The only blunder was the small mathematical, the arithmetic error of giving an equal magnitude to the two arrows. And so maybe Einstein's reaction would have been something like on the cover of Science magazine. Well, the discovery that was initially made with supernovae that were 4 or 5 billion light years away, that meant that in the last 4 or 5 billion years, the universe has been accelerating. If it's being accelerated by something like the cosmological constant, whose effect per unit volume is always the same throughout the history of the universe, then there's a clear prediction. Long ago, when the universe was denser, it should have been slowing down in its expansion. That's because galaxies were closer to each other, so attractive gravity was bigger than it is now, and moreover, the amount of volume between them was smaller, so the cumulative effect of the repulsion would have been smaller. So in a sense, gravity dominated over anti-gravity, and as the universe expanded, one declined, the other got bigger, and at some point in the past, they crossed each other. So the prediction was that early in the history of the universe, it should have been decelerating. So Adam Rees was the principal investigator of a project using the Hubble Space Telescope with which we found more distant examples of supernovae, 6, 7, 8, even 10 billion light years away. And we found that indeed, for the first 9 billion years of its history, the universe was slowing down, and it's only roughly in the last 5 billion years that it has started speeding up. This transition from slowing down to speeding up mathematically is known as a jerk. So in a sense, we measured the cosmos to have gone through a jerk. And the New York Times headline that came out was, "A cosmic jerk that reversed the universe," and there's my former postdoc, Adam Rees. Now, I start getting all these phone calls, "Hey, who's this jerk you work with who reversed the expansion of the universe?" And Adam's mother was not very pleased with this juxtaposition. All right, well, What is the stuff that's causing it? It's not the visible matter in the universe. Visible matter always pulls. Even antimatter, we think, pulls. It's a positive, regular form of energy, although I don't disagree with Tara. It should be measured before we can completely claim that, but everyone believes it pulls. So antimatter is not going to do it. Dark matter doesn't do it either. By the way, there's dark matter there, there. It's not that hard to detect, Tara. There, you know. What's the big deal? No, anyway, we know that there's a bunch of dark matter there precisely because this cluster of galaxies is gravitationally bound. The galaxies are moving around so fast, you can measure that with spectra, that it would quickly disintegrate unless they were bound by extra matter. Indeed, it's the extra matter that causes those speeds. And that argument was actually first made by Fritz Zwicky in the early 1930s, one of my heroes, an astrophysicist at my graduate alma mater, Caltech. He was decades ahead of his time on a number of issues, but he wasn't believed very much and he wasn't well liked, in part because he was arrogant and abrasive and didn't think highly of the intellectual capacity of his Caltech colleagues. Now, he might be showing you here what he thinks of the typical brain size of one of his faculty colleagues. And again, I don't know that that's what he's thinking, but it could be what he's thinking. And he is on record as having referred to his colleagues as spherical bastards, because, you know, they're bastards any way you look at them. A sphere is the only object that looks the same from all directions. I do not encourage you to start referring to your friends as spherical bastards. You will quickly end up friendless. But anyway, Zwicky came to the idea of dark matter in an oblique sort of way. I mean, that's the genesis of it. And then decades later, Vera Rubin came up with the same explanation for the fact that spiral galaxies, which are spinning quickly, don't appear to be disintegrating. And just as Zwicky was ignored for a long, long time, Rubin and her colleagues were ignored as well. But now, as you heard earlier this afternoon, dark matter is like the big thing in astrophysics, eclipsed only, in a sense, by dark energy, the term that has been dreamed up for whatever it is that's causing the acceleration. You know, it's not luminous matter, it's not dark matter, it's not antimatter, it's something. It's some form of energy, but we can't see it, so it's dark, and it's mysterious, so it's dark in that regard too. Dark energy, a term coined by Michael Turner at University of Chicago, a theorist. It's regrettable in a sense, because if there's one equation people have heard of, what's that equation? E equals mc squared, right? Most people have heard of it, even though the actual understanding of it is actually pretty profound and subtle. But I'm continually being asked, are dark energy and dark matter just two sides of the same coin? And the answer is almost certainly not. Dark matter pulls, dark energy pushes. They appear to probably have very different physical origins. But in honor of the discovery of the accelerating expansion of the universe and the implication of dark energy, my wife Noelle made the following t-shirt, which was distributed to members of the Nobel winning teams. Dark energy is the new black. A limited edition. By the way, the other possibility for explaining acceleration is that Einstein's general theory of relativity is incorrect on the largest scales. That's an amazing conclusion as well, if correct. Most theorists seem to be focused on dark energy being the explanation rather than relativity being wrong. But in interest of completeness, let me just mention that. What is the dark energy? Well, we don't know. I think it's probably the vacuum energy. In other words, these little things, virtual particles, are created in pairs and live for a very short time. We know that that happens. Their presence affects the measured energy levels of the electron in a hydrogen atom, for example. But they're fleeting. And it was always thought by physicists that, in a sense, for every positive energy fluctuation, there's a negative energy one, and so the total ends up being zero. Mostly, as you heard during the discussion, because if you do the back of the envelope calculation, you actually come up with an infinite vacuum energy. And you can get it down to 10 to the 120th power with a little trick, or maybe 10 to the 55 power with another little trick. But the point is, it's a real problem, and everyone had assumed that it's zero. But if there's a slight non-cancellation with a positive net energy density, this has the desired effect of expanding space away from gravitational fields like that of Earth faster and faster with time. And all the evidence seems to be consistent with that. But another idea is that dark energy is some new kind of energy associated with a new field, kind of like the Higgs field about which you heard from Tara, but different from it. And it goes by the generic name of quintessence, like the Aristotelian fifth essence. But there are hundreds, if not thousands, of different models. Now you might say, well, wait a minute. Before I close, I've only presented to you evidence from supernovae. What if the technique is flawed? Could be flawed. So, as I said, it's important in science to have other independent techniques, and I won't go into them, but let me just say very briefly that there are now many other techniques, in part measurements of the microwave background radiation, and I believe my colleague George Smoot will be discussing that tomorrow. But a number of different ways of studying the microwave background radiation and the little tiny temperature fluctuations which are associated with density variations in the early universe, they give rise to the same conclusion. And one piece of evidence is that if you take those little tiny density variations when the universe was just 380,000 years old, and you let gravity sculpt the universe for the next 13.8 billion years, and you ignore dark energy, and you do your computer simulations, then you find that the formation of galaxies and clusters of galaxies and voids doesn't quite end up resembling the observed universe now. Whereas if you include dark energy plus gravity and rerun these simulations, then the growth of galaxies and clusters of galaxies and voids ends up now at redshift 0, giving us a structure that actually looks like the observed structure of the universe. Okay? And there are other arguments as well. So in the end, when you put everything together, we come up with this pie chart, a little bit updated using the Planck results, which George will probably discuss, a little bit updated pie diagram compared with what Tara showed. For years, we'd been saying dark energy is 73%, but it's more like 70, it appears. So the dominant stuff of the universe averaged over billion light-year diameter volumes, okay? Not this room, let me emphasize, okay? But giant volumes filled with what we thought was empty space. Well, it's not empty. It's got this dark energy. When you add it all up, it dominates. And we don't really know what it is. For the youngsters among you, if anyone tells you that physics is dead, there's nothing left to be discovered, you tell them, what about 70% of the universe? Nay, what about 95% of the universe? Because most of the remaining is this dark matter, and we don't really know what that is. I think it's probably a WIMP, but I'm not sure. Okay? So we don't really know what 95% of the universe is. We know pretty well 5%. And in fact, the stuff that easily shines, stars and planets and stuff, is only 0.5%. That's the only part we understand well. So in a sense, we're the debris of the universe. We're the afterthought of creation. That's not to say you're not important. You are to yourselves, your family, your friends, your loved ones. But you're not made of the dominant stuff of the universe. The dominant stuff is the dark energy, and we don't know what it is, followed by dark matter, and we know only a little bit more about what that is. And dark energy is also important because it is widely thought to be a quantum scale phenomenon that acts everywhere and thus dictates the dynamics of the universe overall. So it's the one of very few observational tests of quantum theories of gravity or string theories, those theories that are attempting to unify the two great pillars of modern physics, quantum physics, the physics of the very small, and general relativity, the physics of the very large. Any such theory that's incompatible with dark energy or a failure of general relativity can be ruled out as not being a viable candidate theory. So the implications of the acceleration have been extreme. That's why it was awarded, the discovery was awarded the Nobel Prize. And finally then, let me go back to the question I asked, how will the universe end? Well, it's pretty clear that if the dark energy continues to be repulsive, then the universe will expand faster and faster and faster with time as the dark energy dominates more and more over attractive gravity. A runaway universe, so to speak. So if you want to actually see galaxies like this one with your very own eyes through a telescope, you'd better go and look pretty soon in the next few tens of billions of years. Because beyond that time, galaxies will have been whisked away to such great distances that they will be too faint to see, and the universe will be cold and dark and empty. That's what we thought 12 years ago. But theorists like Andre Linde at Stanford and others have pointed out that we don't really know what the dark energy is. And there are models, theoretical models of dark energy, in which the sign changes in the future from one of repulsion to one of attraction. There's a historical precedent for that in the inflation of the early universe. That's something that acted like dark energy when the universe was a tiny blink of an eye old, but then it reverted to an attractive kind of gravity. But maybe, today's dark energy will do that someday. If that's the case, and if there's enough of it, then it turns out that despite accelerating right now, it will someday start decelerating and maybe even will come back. And so there might be a big crunch after all. But I think the data are compatible right now, best with eternal expansion, the cosmological constant, and that we will live in a universe that is a runaway universe, effectively. Well, to close, let me point out that the famous American poet, Robert Frost, in 1920, certainly didn't know about anti-gravity in the accelerating universe. He didn't even really know about the two possibilities of an eternally expanding and a collapsing universe that hadn't been studied in great detail by cosmologists yet. But in the context of, I guess, Dante's Inferno, or some say in the context of a conversation he had with Harlow Shapley, an astronomer who said the sun might blow up or the earth might someday freeze, he came up with a poem that, in retrospect, is relevant to what I had to say right now. It's called Fire and Ice. Some say the world will end in fire. Some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to say that for destruction, ice is also great and would suffice. So you see, in the context of what I discussed today, Frost would prefer a universe that ends in a big crunch, hot and compressed like fire. Hot like fire. Fire isn't compressed, but whatever. But if the universe and he had to perish twice, then eternal expansion and an ending in ice would be okay with him, and that's perhaps appropriate given his name, Robert Frost. Thank you for your attention.
Thank you, Professor Filipenko, for that mind-expanding lecture. We will take a few minutes to gather our panel up front, and at the same time, our ushers will begin to pass out pieces of paper for you to submit questions. Thank you.
Good. Sorry for going a little bit over there.
What's it?
I went a little bit over.
Well, that's okay. I don't think anybody's going to complain.
Yeah. And we have until 5, I guess.
Yeah, we got one section.
So oh, okay. No, I just oh, yeah, okay. Good. All right, good. Yeah. How's that work? Oh, thank you. QR code back, actually.
Okay, folks, please find your seats. We'll get started in just a minute. 1 minute now, okay?
Steve, you look good.
All right, let's begin our questions with members of the panel. Does anyone have a
I'm not very
question
hopeful
on the
about
panel?
experimental
Alex.
clarification either, but we'll see.
Do you want me to go ahead? All right. So first, I want to make a comment about the dark energy, and you can tell them about how wrong it is. But we were there in a small meeting when Mike Turner, we were discussing what should we call it, and the answer that we said, we can't call it the cosmological constant because all the grad students will assume we have the correct answer. Right? So we have to give it a new mysterious name so people actually investigate and understand. And so we tried several different names. I can't remember all of them. But in the end, Mike Turner says we have to call it dark energy because it's clearly an energy. And besides, we want the Department of Energy to pay for part of it. And if it says energy in the name, they will certainly take care of it. And so he's a far-thinking guy, and that's why he's now becoming the president of the APS. He's been very active in not only the theory, but in also making the field progress and being head of many committees. And it's certainly on one of those commissions, he said the study of the acceleration of the universe, which is, we label the dark energy problem, is a really key and critical problem. So you talked about where we are now, but you didn't talk about what we might be doing next. Do you have, I have my own ideas on this, but.
So, right, what to do next? Well, it's a combination of many different measurements that allow us to set constraints on the dark energy or whatever it is that's causing this acceleration. From the supernova perspective, if you measure the expansion history of the universe in greater and greater detail, then you can rule out some ideas for what dark energy is because they will not agree, the predictions for how quantitatively the universe expanded with time will not agree with the observations. So that's one way of doing it, and that's the technique that I and my colleagues are pursuing. We're trying to measure through supernovae the expansion history in more detail. Of course, we have to combine that with measurements of the microwave background, and the Planck measurements, about which I think you'll be talking tomorrow, are certainly very interesting. I'm not sure what's beyond Planck in terms of microwave background, but we need to make those measurements more carefully. We need to do other things like, as you know, measuring the so-called integrated Sachs-Wolf effect. That's an effect where you can see microwave background photons going through superclusters of galaxies. And if there were no dark energy, then it turns out that the photons would gain energy on their way in because they're falling into a gravitational field, and then they would lose exactly the same amount of energy coming out. So you get a net gravitational shift of 0. But because the supercluster expands due to dark energy during the time of flight of the photons across it, the blue shift coming in is a little bit greater than the red shift going out because the cluster has expanded more, on the way out. And so there's a net blue shift. The radiation looks a little bit hotter, So measuring that is another constraint. Measuring X-ray clusters of galaxies provides additional constraints. So it's many, many different constraints that give you this concordance cosmology, as we now call it, to ever greater precision. And one of the interesting things to me is that there are certain tensions that are appearing. The Planck data give a Hubble constant, this expansion rate of the universe right now, which is significantly lower than what we have measured using, Cepheid variables in relatively nearby galaxies. And so not everything is rosy, and this is actually good. It's a little bit like Tara said, that if you find things that are unexpected, that might lead to a whole new discovery. So we'll see as the data get better and better.
But
the dark energy, the JDEM mission and, all these things, I guess now it's called WFIRST, if it ever gets built, given the state of the economy, will help. And there's a European mission called Euclid that'll help. Measuring gravitational lensing of galaxies is another way of getting additional constraints. So there are many different types of observations that we hope will let us home in on whether this really is the cosmological constant or something else.
Yeah, I think that when it's really exciting when there are little discordant results, but again, I want to go back to my result that some of the results are wrong. They're all, the Hubble constant itself, as you know, if you look at history, was measured to be 100 with 10% accuracy and 50 with 10% accuracy, and instead it'd be 75.
We think we're better than
and
that.
Then we say, no, exactly. But so I want us to be careful about this. But it's what is a little what may happen, and while I don't like to predict anything that's less than 1 trillion years from now. It could be a little like particle physics, as Frank and Tara were saying. I mean, the standard model works just too well, and that's been a big frustration in particle physics for many, many years. And this picture of a cosmological constant, unfortunately, everything seems to be coming down to it. But unfortunately, that's the one value where you really can't say what it is. And it could be that it's quite possible that while we've had this incredible period of discovery, that we have this model that we can't understand that explains all the data, and it may continue. My bet is that we'll see that everything is going to be consistent with this model that isn't explainable for the foreseeable future.
Yeah, it could become so difficult and so expensive to show a difference from the prediction of the cosmological constant that effectively we can't reach that kind of precision.
It would have been easier if it hadn't been, because then it would be easier. But it looks
that's right.
It looks like one and walks like one, and make act like one.
Right.
Yeah.
So I actually think that this is another reason for the multiverse idea. The vacuum energy can be pretty much anything.
Well, we'll talk about that.
And we don't live in a universe with a high vacuum energy because stars and galaxies wouldn't have formed. But we don't live in a universe with zero vacuum energy because out of the continuum of numbers, 0 is a very unlikely number, as is any other single number. But the point is we live in a low vacuum energy universe, and that was conducive for the development of complexity. So I'm okay with that, but I can't prove it, and it leaves me in a dissatisfied state.
It should.
Yep, it does. Good. We're in agreement, Lawrence.
Professor Shears has a question.
So, Alexei, you also mentioned that it might be possible that Einstein's theory of general relativity might fail at these really large distance scales that we haven't been able to test.
Yeah.
But you said that people didn't really like that.
Yeah, the failure of general relativity is a possibility, but general relativity is such a beautiful theory. It's based on the most simple assumption. I mean, beyond special relativity, which just assumes that you can't tell if you're moving at a uniform speed, and the speed of light is independent of your motion or the motion of the emitter, and that's an experimentally testable fact. Those two things lead to special relativity, and then the principle of equivalence, the idea that you can't tell whether you're in an elevator accelerating upward or in a gravitational field pointing downward. And any of you who have been in an elevator, you kind of feel heavier when it first starts accelerating. How do you know the Earth's mass didn't become bigger for a bit? That's the principle of equivalence. And that is such a obvious and measured thing, from which all of general relativity falls, right? And then the mathematical framework that comes out of that is so pretty that many of us just are reluctant to abandon general relativity. But it's definitely a possibility that it may be wrong. It's just that I think most theorists, if you look at the numbers of papers that are written, there are many, many more papers exploring the possibility of dark energy versus those exploring the possible failure of general relativity.
General relativity is very difficult to modify in a consistent way. Most attempts fail with very gross confrontation with experiment. So I think many theorists have tried to modify general relativity, but most of those attempts never leave the desk drawers in the end. They don't go public because they're obvious failures.
There's another reason. Indeed, in fact, most of those modifications are far uglier than the possibility of dark energy, I think, for most theorists. There's two other things. We think that really at small scales, at very small scales, that general relativity probably will change when we have to introduce quantum mechanics.
Right.
But so it's not just that it's hard to change theoretically. The question is, why does it suddenly change on a scale of galaxies?
Yeah.
And that sort of seems kind of arbitrary.
Right.
If you put fundamental physics constants together, it's not a natural scale to change. Now, some people have argued that, well, there is one other scale, which is the size of the universe, and maybe there may be some, could be evidence of something outside of our universe, and you make those hand-waving arguments.
Right.
But from a fundamental physics perspective, it's not you wouldn't, if you locked a physicist in a room and asked her, what scale would general relativity change on? She wouldn't say the scale that we measure it to be. So I think that's another fact.
Nevertheless, just as a final point on this issue before moving on, I must confess that occasionally at 3 in the morning I wake up screaming. My wife can attest to this. Because I'm concerned that dark energy and dark matter may be our modern day equivalents of Ptolemaic epicycles. Remember, Ptolemy had the idea based on Aristotelian physics that essentially everything circles the Earth, but to get the predicted positions of planets to match the observed positions of planets, you had to have these extra little epicycles, these little orbits. And if he added epicycles on top of epicycles, he could have achieved arbitrarily good agreement with the data. Because in fact, any periodic function can be decomposed into a sum of sines and cosines of different amplitude and phase. This is, for those studying mathematics, you may recognize this as being Fourier analysis, okay? So in a sense, he was inventing Fourier analysis, so it was mathematically brilliant and arbitrarily good agreement with observations, yet we now know fundamentally wrong. So I do worry sometimes.
I would also like to add a bit of historical perspective. In the past, there have been theories that look extremely well established. far better established than our current cosmological standard model. Like Newtonian gravity. Newtonian gravity went from triumph to triumph, among other things, solving an earlier dark matter problem when the gravity acting on the planet Uranus seemed to be wrong.
Yeah.
And people used that to predict the new planet, Neptune, which was subsequently found. Similarly, the wave theory of light in the 19th century was a great triumph and had mountains of experimental evidence and even a profound theory with Maxwell's equations and electromagnetism. Nevertheless, it was drastically modified in the 20th century. Both of those things were drastically modified in the 20th century. Newton's gravity eventually gave way to Einstein's, and the wave theory of light had to be generalized to incorporate quantum mechanics. So we may be in a situation like that. But what I think is true is that a modification of gravity will have to be profound. Little tricks and ugly fixes are not worthy and are unlikely to agree with the vast body of data that is accumulated.
I want to add one thing, Frank, just because I worry, because I get lots of letters, you probably do too, from people who say, you know, everyone thought Einstein was crazy. People think I'm crazy, therefore I'm Einstein.
Great logic.
But the idea is that some people think that, okay, all these fundamental theories have been overthrown, and I can show everything's wrong. And the really important thing for people to realize is that Newton's law of gravity isn't wrong. It's right. It works very, very well, and NASA uses it a lot. And intercontinental ballistic missiles depend on it, and all sorts of stuff that affect our lives. And similarly, the wave theory of light isn't wrong. We modify our understanding at some level, but those explanations which have satisfied the test of experiment still are valid, and that's a really important part of the continuity of science.
Yeah, I also like to say that when we can, we try to tweak things and add things rather than considering radically different changes in successful theories. So certainly in the case of dark matter as opposed to dark energy, it's very plausible that it's just a new kind of particle of some kind, either an axion or a WIMP or some other kind of new particle. And although there have been attempts to mimic the effects of dark matter by changing gravity, I think those are widely regarded as silly at this point. If there's a more conservative fix, that should certainly be explored fully.
I think Professor Ting has a question.
Yeah, I just wondering, would you like to make a comment? Why it happened 5 billion years ago?
Yeah, why did it happen 5 billion years ago that this rough equality between gravity and anti-gravity, if you will, occurred? Yeah. So that's one of the big cosmic questions. It's part of the reason many theorists don't like the cosmological constant. First, the fact that it's a very small value, but not quite zero. That's very weird. And then the fact that there's this rough equality, 0.7 versus 0.3. That's roughly 50-50. It could have been 100 to 1. It could have been a quadrillion to 1. It could have been a Google to 1. You know, why is it 50-50? And I don't know. You know, it's the why here, why now problem that Michael Turner talks about.
Yeah, I'll talk about
the Tanya Harding problem. Yeah. Some of you are old enough to remember that, you know, right? You know.
We'll probably hear about that from Professor Krauss tomorrow.
Yeah, but we don't really know. But we do know it couldn't have been a very large cosmological constant if that's what it is, because then stars and galaxies would not have formed. And it's a pretty small value. It could have been smaller, but 0 is simply unlikely, you know, out of the continuum of numbers. So an anthropic type argument, which Steven Weinberg actually did make in the late 1980s. He made this argument that, you know, clearly the cosmological constant isn't more than 100 in some units, the units I've been using, because otherwise we wouldn't be here. And he was right, you know. Yeah.
Good.
But 0 is a much more beautiful number.
0 is more beautiful, except that no theorists have come up with the exact cancellation that would get, you know, right?
Yeah, but everyone thought it was, and we should point out that a universe in which it was 0 would be nicer than the universe we live in. I had this debate with several fundamentalists, and maybe I'll get into that.
Professor Coyne has a question.
Yeah, why do all type 1a supernova more or less have the same energy output?
Yeah, the type 1as are all more or less the same,
Especially considering it's very cataclysmic exchange.
Yeah, it's cataclysmic, but it occurs at or near the same mass, the Chandrasekhar limit, each time. Yeah. It becomes unstable at that point. You get a runaway set of nuclear reactions. Now, to be fair, we're finding all kinds of weirdo supernovae recently that don't seem to fit in that paradigm. So there may be ways in which the surface layers of a white dwarf can explode more than they do in what is called a nova explosion. This would be a supernova as opposed to a supernova, right, or a nova, right? Anyway, in between a nova and a supernova. We're getting into the fine details here. But it appears that many, if not most, of the white dwarfs that do explode with a high luminosity do so at or near the Chandra limit.
Good, thank you.
Your time? No time.
Okay, folks, I think we'll have to cut it off at this point. I know there are a lot of questions. We took a lot of questions from the audience, and I know your folks are going to be disappointed that we're not going to be able to get to those. I'm going to offer that we will make copies of the questions and try to answer them on the internet. So watch the Nobel Conference website in the near future for answers to some of those questions. And at this point, I think we should adjourn and reconvene at 6:30 for Professor Ting's talk. Thank you. So please find some seats. I hope everyone had a great lunch. I know I did. It was fun seeing old friends and meeting some new ones. We have an exciting afternoon planned, and we're going to get it started here. It's my pleasure now to introduce my colleague, Professor Josh Brown from our philosophy department.
So our next speaker is Dr. Tara Shears. She's professor of physics at the University of Liverpool and a member of the LHC-B experiment at CERN's Large Hadron Collider, the LHC, where she initiated the QCD Electroweak and Exotica Physics Working Group. She's also one of the world's foremost public ambassadors for the LHC and for the science of particle physics more generally. Now, I am really excited to introduce Dr. Shears because she's got the coolest job in the world. She smashes protons together at just shy of the speed of light and then sifts through the wreckage in order to look for clues about the nature of matter and about the evolution of the early universe. It's a little bit like this.
Let's get down to business. Are you ready?
I'm ready.
Do you mind if I flip the switch?
Go for it.
This is Compact Rocket Sled in 3, 2, 1. Wow!
Now, as I said, it's a little bit like this, but really, it's even cooler. Because, protons, of course, are much smaller than the Mythbusters rocket sled. But the protons that Dr. Shears smashes together are also moving much, much faster. The rocket sled is moving at about 650 miles an hour. That's faster than most passenger jets, and were you riding that sled, you could get from here on Gustavus's campus to downtown Minneapolis in about 6.5 minutes, or from the LHC in Geneva to Stockholm in about 2 hours. The protons in the LHC are traveling over 1 million times faster, roughly 616,600 miles per hour. In your 6.5-minute rocket sled ride to the Twin Cities, an LHC proton could travel to Mars and halfway back, over 71 million miles. The proton gets from the LHC to Stockholm in 7/1000ths of a second. Now, when two of these protons collide, they don't just disintegrate like the car in the video. They briefly recreate the conditions that prevailed in the universe right after the Big Bang. A stew of particles with a temperature of over 2.5 trillion degrees Fahrenheit, hotter even than the center of the sun. Dr. Shears studies the birth and behavior of fundamental particles in this stew. Just this past spring, in April, Dr. Shears' LHCb experiment announced exciting results concerning a type of particle called a strange beauty meson. Now, what's really fascinating about strange beauty mesons is that they spontaneously can flip from being matter to being antimatter. The LHCb experiment looked at 70 trillion proton-proton collisions, isolated 1,000 or so strange beauty mesons, and discovered that matter mesons outnumbered antimatter mesons by about 25%. This is the first observation of what's called a charge parity, or CP, violation in strange beauty mesons. And it's one important experimental step in helping us understand why, when we look out to the farthest reaches of the universe, and so back in time towards the Big Bang, we see only matter and not antimatter. Dr. Shears' work thus reaches towards all of the disparate limits of the universe. By probing its smallest, most fundamental parts, she's helping explain its largest features and discover what it was like at its very beginning. Please join me in welcoming Dr. Tara Shears.
Thank you, everyone. So, in this talk, we're going to explore the universe right at the innermost frontiers. We're going to look at what matter is made of and how it behaves at the very smallest, the very deepest scales, the scales of particle physics. Now, what I want to do is to show you what particle physics has shown us, but I don't just want to talk about what we understand about the universe at these very tiny distance scales, because I also want to show you, in a sense, how little we understand and where the frontiers of our understanding lie. So I'm going to tell you about some of the biggest open questions in our subject. These are questions that drive us to do our research. They drive us to build enormous experimental facilities to try and find answers. And I'm going to tell you about one of those. I'm going to tell you a little bit about the Large Hadron Collider, because I work on it. It's most familiar to me. I'll show you what it looks like, how it works, but most importantly, I'll show you our latest results, because already the Large Hadron Collider is starting to fill in the gaps in our understanding of matter and the universe at these innermost scales. And so you'll see for yourselves just how far we've come and where the frontiers of our understanding have stretched to. Now, let me start at the beginning, because I should tell you really what particle physics is and how it fits into the history of the entire universe. So, in brief, particle physics, in particle physics, we have an idea that everything that we see around us is made of the same basic stuff, the same ingredients, the same fundamental particles that make everything. And we think that only if we could identify these and understand their behavior, well then, that would allow us to understand the behavior of the universe at larger scales. And that's the approach we take. Now, behind me, you can see almost everything we know about the universe through physics encapsulated in one picture, very simplistically. So on the left, we have the Big Bang, where we think everything started. The Big Bang was this, if you like to imagine it, was a hugely, tremendously energetic fireball that brought everything in the universe into existence. And the early universe was a very different place to the universe that we know now. It didn't have stars in, it didn't have planets, it didn't even have atoms. Instead, it was populated just by the ingredients of atoms, the fundamental particles that I just talked about. Now, as time marched on, the universe expanded and cooled down until, at various points, as it cooled, it became, energetically speaking, more effective for matter to start to clump together into new forms. So after a few fractions of a second, we start getting neutrons, protons. After a few 100,000 years, we have the first atoms. And then, as time marches on, we get larger and larger structures, stars, galaxies. And then, here we are, almost 14 billion years later. Well, that's what we think happened. But of course, how we know any of this, and I say this because I'm an experimental physicist, is through experiment. It's the only way to be sure. And to work out what the universe is made of now, it's quite straightforward. You can just look at it. You look at it through telescopes. You can send out probes to take measurements of anything if it's close enough to you. But if you really, really want to understand the universe, you also have to understand how it got from the Big Bang to now. And that's a problem, because you can't look at the very early universe through telescopes. It's opaque. You can't see into the universe before it was about 300,000 years old, when atoms formed. So instead, if you want to work out what was going on just after the Big Bang, you have to recreate those incredibly hot conditions in the laboratory. And that's what we do in particle physics. That's what we do in our particle accelerators. So that's the angle, if you like, that particle physics brings to our understanding of the universe. It tells us what matter is made of at the very tiniest scales, what the universe is made of, but also what the universe was doing in the first brief seconds of its existence. Now, already, our experiments have shown us an awful lot about what the universe is made of. So we've realized that matter is made of no more than 12 fundamental types of particles, 6 quarks, 6 leptons. Now, these particles are really amazingly small. They're at least as small compared to atoms as atoms are compared to you. And I say at least as small because they're so small we've never been able to measure them. That's just the limit of technology. They are incredibly small. Now, in your everyday lives on Earth, you don't even see this many particles. You don't come across them. You just come across a fraction of them. The first 2 quarks up there, the up and down quarks, they're familiar to us in everyday life because collections of those form the neutrons and protons in our nuclei, which are orbited by electrons to make atoms. And the neutrino associated with the electron we often see in radioactive decay. We don't even come across these other more exotic particles unless we go to higher energies than we typically have around us on Earth. But they exist, and we've seen them in our experiments. We know they're an ingredient of the universe. OK, so that's matter. That was easy. Now, what makes this matter set of fundamental particles stick together to form matter that looks and behaves in the way it does to us are a small number of fundamental forces. Not very many, just a small number. There's a weak force, for example. Now, it's the weak force's job to give us radioactive decay. The weak force describes radioactive decay. And it affects every single one of our matter particles. And we think that we have a picture for the way this force works. We think it's communicated by the exchange of other types of particles that carry the force, force-carrying particles, called W and Z bosons in this case. And this idea of a force working by exchanging a force-carrying particle between matter particles isn't just peculiar to the weak force. It's the idea we have for how forces work for really any of the forces that we can describe. So besides the weak force, we have another couple to get through. There's the electromagnetic force, which is much more familiar to us. It's driving the lights, it's driving the projector. You use it at home an awful lot. You know it acts on anything with an electrical charge. And that means it acts on any of our fundamental particles that are electrically charged too. And it's communicated by photons of light. And then quarks, and this is what makes them different from leptons, as Frank was telling us in his talk before, experience the strong force. And it's the strong force that keeps atomic nuclei stable, because it's an attractive force. And it's strong enough to overcome the electrostatic repulsion between the protons that you have in the nucleus that would otherwise drive it apart. And that's communicated by a number of force-carrying particles called gluons. Fantastic. And I have to say, that's almost all we consider in particle physics. That's almost all the ingredients of the universe that we've come across. Now, there is one more fundamental force that I haven't mentioned. And I don't know if you can think of what that might be, but it's a force that's responsible for the large-scale structure of the universe. It's gravity, of course. Gravity is incredibly important. Gravity acts on mass. It's what is keeping you stuck to your seats, stuck to the Earth. And we know that all of our fundamental particles have mass as well, because we've measured it. So therefore, they must also feel gravity too. However, gravity is so much weaker than the other forces that we can just neglect its effects when we're describing what goes on in the very small distance scales that we look at in particle physics. So I have it here with a question mark, because gravity, although we know it exists, it clearly does, is something that in our subject we have yet to fully understand. Okay, so we have matter, we have forces, and there's just one more ingredient left in the universe. And it's an ingredient that was only verified by a discovery last year. It's a very timely piece of information. And this extra piece of the universe goes back to this idea of mass that I just mentioned for gravity. Why do particles have mass? What causes them to have the value of mass that they do? Well, we think the explanation lies in something called the Higgs field. Now, the Higgs field is like a type of energy field which is present throughout the universe. It's part of the universe's structure. And fundamental particles, we think, obtain mass as they move through the universe and move through the Higgs field. And the amount of mass they get just depends on how strong their interaction with that field is. And this field also has a particle associated with it, which is the Higgs boson, which was what was discovered last year, which is what allowed us to verify that this particular idea was correct. So in this idea, if you're a massless particle like a photon, you zip through the universe completely unaware of the Higgs field. But if you're a massive particle like the top quark, your path through the universe is impeded by your interaction with this field all around you. You are a heavy object. Now, we don't see the Higgs field, it's invisible. But we should be able to see the Higgs boson that's predicted to accompany it. We should be able to make it in our experiments. We should be able to detect it by the characteristic way it decays and leaves a signature behind. And indeed, that is the layer of logic that we followed in order to make the discovery. And I'll tell you a little bit about how that worked later on. Okay, we have mass, force, and an explanation for mass. And we even have a picture for how this all works together. And what's even better than that is that we can encapsulate this picture in mathematics. We can write it down in equations. And the equations that we write down form our theory of particle physics. And our theory of particle physics is so succinct, so elegant, that you can write it on the front of a T-shirt. And if you go to CERN over in Europe, you can even buy the T-shirt. It is a retail opportunity that awaits you as you go in the front door. I've always wanted one of these. And the reason that this equation is so beautiful harks back to what Frank was saying in his talk, because it's founded on the principles of mathematical beauty that he was talking about. So now you're starting to see where the frontiers of mathematics and geometric structure start to impinge on the world of reality and what we can measure. Now, not only is this equation really, really beautiful, it's also really, really good, because we haven't yet made any measurement at all that disagrees with any of its predictions. It's so good that we call it the standard model of particle physics. And that's brilliant. But it's not the whole story. It's not the whole story because we know that this theory is incomplete. For a start, it doesn't describe gravity. And that's not because we've been lazy and we think it doesn't matter. It's because we can't put gravity in the same type of equations as the other forces. It just doesn't work. It gives us rubbish out as answers. And besides not describing that, we know that there are many phenomena in the universe that we have observed, but which cannot be explained or predicted inside our theory. And for that reason, we think there must be a deeper, underlying understanding of the universe to be had, if only we can find it. And it's that that drives our research, to learn more and to understand more about this innermost layer of the universe. So, having told you about what we understand, I'm now going to move on to what we don't understand. And so the very fact that I've spent such a small fraction of my talk on what we understand should tell you that the entire universe is up for grabs when it comes for understanding it. There's so much to find out. I'm just going to tell you about some of the bigger questions that we have. The first one is such a basic question that I've given it number 0, not even number 1. And that's, is the standard model even correct? We know it's incomplete, but where it can describe data, is it even a correct description of data? Now, this was a much more leading question before the LHC started, because the standard model had a prediction for finding the Higgs boson. The Higgs boson hadn't been found, and the whole correctness of the standard model hinged on this particle being discovered and being known to be there, and being known to be the particle associated with the standard model. That would be the only way to verify this. Well, we have found Higgs, and not just the theorist, Peter Higgs himself. We have found a Higgs boson, but we still don't know very much about it. We still don't know if it's a Higgs boson we expect to see in the standard model, or a Higgs boson that's associated with some more exotic theory of nature. So that's why I've kept this question in my talk, and I haven't deleted not knowing if the theory is correct or not yet, because although we're close to the answer here, we don't entirely know, and I'll show you how close we've got later on. Okay, so let me talk about something that we really don't understand. And in fact, Josh beat me to it in his introduction. And this is the phenomena of antimatter. Now, antimatter sounds great. It sounds like science fiction, but it's not science fiction. It's actually science fact. It's just incredibly rare. Now, every type of particle I've told you about in the standard model has an antimatter counterpart, a type of mirror image, oppositely charged version. Now, we just don't see very much antimatter on Earth, and we know this because if I have antimatter and it meets its matter equivalent, it annihilates, and the resulting annihilation is huge. If I have 1/4 of a gram of antimatter meeting 1/4 of a gram of normal matter, this annihilation has the explosive force of 5 kilotons of TNT. It's a very good diagnostic tool if you have antimatter in the room. You immediately discover it. Well, we haven't seen that. We haven't seen it on Earth. We haven't seen it out in the universe anywhere we've looked. And so for that reason, we don't think there's very much antimatter around. And that is the problem. Because when the universe started in the Big Bang, we think that half of it was made of antimatter. And just after the Big Bang, matter and antimatter would meet, annihilate, releasing photons of light that then would split into new pairs of matter and antimatter that would meet, annihilate. And this whole process carried on as the universe expanded and cooled. Until eventually, when the universe was a matter of seconds old, the universe had expanded so much and cooled so much that these annihilation photons no longer had enough energy to make new pairs of matter-antimatter particles. And this whole battle between matter and antimatter stopped at that point. And what remains in the universe now, today, is a consequence of a very tiny difference between the amount of matter and antimatter that we had at that point. A very tiny difference, something like 1 part in a billion. But that very tiny difference is the reason why we're here. We're the leftovers. Because if there were equal amounts of matter and antimatter at that time, the universe now would just be full of light. It would be a very, very different place. So if we really do need to understand how the universe evolved, and that means we really do need to understand what made antimatter that little bit different to normal matter, what that little difference in behavior is. And that is one of the leading questions in particle physics today that we have to solve. But it's not the only one. So not only are we not 100% sure that our theory is correct, not only do we still have to understand how the universe evolved, everything I've told you about concerns visible matter. And cosmologists tell us that's a mere 4% or so of the whole thing. So in fact, what I've described to you is a small fraction of the universe. There's far more out there, and you'll be hearing about it in talks after mine. The vast majority of the universe's energy budget consists of mysterious dark energy and mysterious dark matter. Now, in particle physics, we have absolutely no idea what dark energy is. We have no idea what dark matter is either, if I'm perfectly honest. But at least we have some ways of testing what dark matter might be made of. We have ideas, we have possible alternative theories of matter that hypothesize what it could be composed of that we can test in our experiments. And one of the most popular versions of theories that could explain this is a theory called supersymmetry. We talked about it very briefly in the discussion after Frank's talk. Supersymmetry is a theory that takes the standard model and extends it. And it brings in deep, intimate connections between force and matter. And in the process, it predicts the existence of a whole new raft of particles, supersymmetric or SUSY particles, partners of the particles that we know about. And the supersymmetric partners of matter particles behave like force-carrying particles, and the supersymmetric partners of force-carrying particles behave like matter particles. Now, the really great thing about supersymmetry from the point of view of trying to work out what dark matter might be made of is that in many versions of supersymmetry theory, the lightest one of these new particles is a really good candidate for dark matter. It's a really good candidate because it's massive, so it experiences the gravitational effects that led us to infer the existence of dark matter in the first place. And it's also a really good candidate because it's completely, experimentally unseeable, just like dark matter. Well, that seems rubbish. Why would you explain something you can't see by predicting something you can't see either? But it's not that bad. Because if supersymmetry is the right way to view the universe, although we wouldn't see the dark matter particle, we would expect to see the other supersymmetric particles predicted by the theory. We should be able to discover them in our experiments, measure their behavior, match that behavior up to what we expect to see with supersymmetry. And if we can do that, we can infer the existence of this lightest dark matter particle. We can infer what dark matter would be composed of, and that would be wonderful. So these are pretty big questions, but they're by no means the only questions. There are many, many fundamental questions. And these are just the known unknowns. We don't even know what the unknown unknowns are yet. Because what we found out is the more we discover about the universe, the more we find out there is to know about it. And it's questions like this that make us want to research the answers. It's questions like this that made me want to become an experimental particle physicist, because I wanted to know why. So, how do you find answers? Well, if you're an experimental particle physicist, you need an experiment to work on. And there aren't many particle physics experiments in the world. I have a map of the globe here with some of the main ones, and I stress this is a personal selection, so if I've missed out your favorite experiment, I'm very sorry. So the places in red are where we have particle accelerators. So there's Fermilab and Brookhaven in the States, CERN in Europe, KEK in Japan. Some of these have neutrino facilities as well. Neutrinos, we don't know very much about. They need specialist detections, specialist experiments. And I've put some other facilities where neutrino experiments take place in blue on the map as well. So you pick one of these places. You pick the experiment that's going to give you access to the data that you need to explore these questions. And I work at CERN, which I'll tell you about now. It's a European Centre for Particle Physics. And it's been researching fundamental physics now for almost 60 years. And during that time, it's moved from being a European centre set up just after the Second World War to allow physicists from different countries to be able to collaborate together when normally politics would not allow them to now being something more of a world centre, because particle physicists from all over the world, from here, from Australia, from Africa, from India, all come to CERN to collaborate together and perform their experiments. And that's because CERN is an incredibly exciting place at the moment, because it's the home of our largest, most powerful particle accelerator. It's the home of the LHC, the Large Hadron Collider. Now, you may have heard of this before, but if you haven't, I'm going to tell you all about it. So the LHC, you can see it in this picture behind me, actually on either side. I've just realized there's two screens, so I should stand in the middle. On this aerial view, in red, you can see the outline of the LHC itself. It's a circular accelerator, and I'm mixing up my units here between metric and imperial. It's about 16 miles long, 27 kilometers. And it straddles the French-Swiss border near Geneva. So if you can see a dark area just above the ring, that's Lake Geneva. The city of Geneva is just at the right-hand end of that before you get to the mountains. And in the background, you see the snowy Alps. And Mont Blanc, the tallest mountain in Europe, is slap bang in the middle there. Now, the LHC is situated 100 meters under the ground, 110 yards. I looked it up. I did the translation. If you go to CERN, ever, if you find yourself in that area of Europe, you can go and visit it. As long as we're not running, you can actually go underground and visit it. And by the way, this year and the next year is a very good time because we're not running. And if you do that, you'll find yourself standing in a tunnel like this. And it's only by standing in this tunnel that you really appreciate just how very large the LHC is. You can just see it curving away in the distance. Hardly at all. It's almost like a straight line. The circle is that big. And you find yourself standing next to a long chain of blue magnets. Well, these magnets are the heart of the particle accelerator. It's their job to keep our particle beams bent round in this circular path. Because what happens when the LHC operates is that we have two beams of protons, hydrogen nuclei, circulating in opposite directions around the accelerator, and then accelerated to enormous energies. Until at design spec, these beams will be going just a few miles an hour less than the speed of light. Incredible. Now, I have to add, we haven't reached design spec yet. We're only halfway there, but it's still extremely fast. And when we've made the beams go this fast, we bring them together and we smash them into each other at 4 points around the ring. It's not quite as good visually as Josh's video, but it's still pretty effective. And we don't just do this once or twice. This process goes on 40 million times a second. And what's so amazing about that, what's so fascinating and compelling if you're a particle physicist, is that in every one of those collisions, for a tiny instant of time, in the tiniest area of space, what you've done is recreate the very hot conditions of the very early universe. And that means you can study matter as it existed at that point in the universe in terms of fundamental particles. That's how we get them to study them. And when I say very early universe, I do mean incredibly early. We're talking billionths of a second after the Big Bang. This is where we can access experimentally. Now, around these collision points, we build our experiments. And our experiments are like gigantic, three-dimensional digital cameras. And they allow us to take a snapshot of what happens during a collision. They allow us to take a snapshot of the fundamental particles that are produced and what happens as they fly outwards. We record their paths, their energies, everything we need to be able to deduce what's going on there. And the idea is, if we keep on taking snapshots of what goes on in the early universe and what goes on at matter at these very tiny levels, we can start to build up a bigger picture of what's happening. And we can compare it to our theory of what should be happening. And if it matches, great, fantastic. We understand what we're looking at. And if it doesn't, oh, that's even better. We're going to make a discovery. You can't lose in particle physics. Now, just like the LHC, our experiments are huge as well. This is a picture that you may have seen sometimes in stories in the media, often where CERN stories come up. It's a picture of the ATLAS experiment, one of the two big experiments. CMS is the other one. America works on both of them. But it's a picture taken during construction. So all you can see here are the orange-striped rings of the magnet held up by scaffolding. The important point here, and this is why I wanted to show you this picture, is to take note of the normal-sized man in the yellow hard hat standing at the front. That gives you the sense of scale for just how very large this experiment is. It's 20 meters high. It's 45 meters long. Now, if you see it, that entire volume is filled with precision particle detection equipment, with some 100 million channels of electronic information to read out every time we take a snapshot. It's extremely high-tech, extremely complex. Now, every experiment at the LHC is instrumented in the same way, using the same sort of ideas. So what we do immediately around the collision point is have a series of detectors that can tell us where particles go. Incredibly precise detectors, like this silicon-based detector we built for my experiment, LHCb. The silicon is a silver semicircle, and it's the size that would just fit in the palm of your hand. And it's so precise, it can tell you the position of a charged particle going through it within 1/10 of the thickness of your hair. And every experiment has its own version of this, a whole series of them that provide the dots we join together to trace out the paths of particles. Around this, we have other detectors that measure other features of the particles, how much energy they have, what type of particles they are, until by the time you get out to the edge of the experiments, these detectors get very large indeed. And what you see behind me here is a picture of one of the outermost detectors in the ATLAS experiment being cabled up, finished off before we started data taking. Now, I wanted to show you this just to prove that we had filled the middle of ATLAS with particle detection equipment, and we hadn't left it empty. If you can turn your brain round from where you saw the detector before, you're looking at it end on now, but you can still see those orange stripy magnets. But now they're buried inside lots and lots of detector material. You can also see two physicists cabling up the last part of this detector. But note, to get there, they're on a platform. And the platform is suspended by a crane 20 meters above the surface of the cavern that the experiment sits on. You really need a good head for heights if you're going to work on a particle physics experiment. Now, not every experiment is as big as ATLAS, but as I say, they all work on the same principles. The LHC gives us a collision that makes the fundamental particles that we study. The experiments take a snapshot, and different particles leave different traces inside the experiment, depending on how far they travel before they're absorbed. And that's what allows us to recognize them. So if we read this out, we can write software programs to analyze what we're seeing. And then, if we do that, we can compare what we get out of these software programs to our theory to see if we're on the right track or not. So there's one extra ingredient we need before we can look at the data, of course, and that's the computers needed to manipulate the vast amount of data that these experiments produce. They produce petabytes of data. In 1 year, they should produce 1,000 times more information than the world annual book production. You know, no one's got enough computers to analyze that. And that presents a bit of a problem, because you do have to analyze a data set of that size if you're going to research any of the big questions I told you about in the beginning. If you want to find the Higgs, if you want to look for dark matter, you need to look through every single bit of that data. But we have a solution, and it was developed by computer scientists. The solution is called the grid, and it's like the next step up from the World Wide Web. It's a layer of software that we put on our computers that make it, from the outside to the user, look like all of our computers in particle physics are joined together in a way we just are completely unaware of. And it makes our computing facilities behave like a geographically distributed supercomputer that is powerful enough to meet our data processing needs. And this map of the world, wherever it has a blob, shows you where we've put computers and connected them onto the grid. And wherever you see a little line, that's where someone's written a program, a software program, and it's traveling around the computer looking for the data, or it's sending back its results. We spend hours looking at maps like this, wondering how our programs manage to get to exotic places when we don't. But it's the last step in our puzzle. So the LHC gives us fundamental particles. The experiments give us snapshots like this. And it's the grid that gives us the computing power to be able to turn this snapshot into an analysis that tells us that this is a candidate, for example, as it is, to be a Higgs boson. So that's how we do it. That's how we perform our research. That's the idea behind it. And the LHC has been running, I mean, really seriously running, since about 2010. And it's given us a huge amount of data, hundreds of trillions of proton-proton collisions. So now I want to go back to the big questions that I told you about at the beginning of the talk. And I want to show you how much progress the LHC has helped us make into finding out more about the universe. You know, let's tie it back and see how we're doing. So remember the first question. Was the theory correct? And that was all tied up with whether the Higgs boson existed, and if it did exist, was it a Higgs boson? Was it the sort of particle we expected to see in the standard model? Well, prior to the LHC, nobody had discovered the Higgs. Lots of experiments had looked for it, including at the Tevatron here in Chicago, but no one had seen it. All these experiments could do could home in on a certain region where, if the Higgs boson did exist, well, that would be where we'd expect to see it. It would have a mass in this region here. And that's what allowed the LHC to be designed in such a way that if that Higgs boson existed, then it should be discovered. So up until the LHC, your best chance of finding the Higgs, if you didn't bump into the man himself, was to buy the soft toy version. And I dread to think how this got started. I have this awful vision of 100 or so PhD students who are so fed up by having a PhD on finding the Higgs and then failing to do it that they're driven to doing things like this. But at least, well, at least it was less expensive than a genuine Higgs boson. But all that changed when the LHC started, because the LHC had enough energy and produced enough data to be able to disentangle traces of the Higgs boson from all the many backgrounds that mimicked the signal, that messed up the signal for other experiments that went before it. And just over a year ago, on a date that Europeans now refer to as Higgs Dependence Day, I can say this because I'm European, then CERN held a public seminar where the ATLAS and CMS experiments that were driving the search for the Higgs publicly announced their latest findings. And this is what they said. Now, I'm going to have to do a little bit of translation from particle physics language, I think. So what had happened was hundreds of trillions of proton-proton collisions had been analyzed, and a new particle had genuinely been seen. And it had a mass of about 125 times the mass of the proton, where nothing else existed before. And it was seen at 4.9 standard deviation significance. Now, in particle physics, I have to explain this. It's a little bit embarrassing. We have a threshold where we officially define when something has been discovered and when it hasn't yet been discovered. And this threshold is really a matter of statistical precision. And our threshold happens to be 5 standard deviations. And so no particle physicist could really put the word discovery on that slide there. Now, the difference is 5 standard deviations just corresponds to a chance of 1 in 1.7 million that nature has somehow conspired to look like the thing that you're looking for without it being there. 4.9 standard deviations is only a chance of 1 in 1 million, you know, quite different. But luckily, the media were on hand to translate for us. And this was widely reported as a discovery, as indeed it should have been, because both experiments independently saw the same behavior. They saw the same signal from independent data sets analyzed independently. That's a very strong confirmation that something new has happened. And indeed, no particle physicist present at CERN at that time was in any doubt that the Higgs had been discovered. And CERN weren't in any doubt either, because sneakily, they had invited some of the theorists responsible for predicting the Higgs mechanism along to the seminar, just in case they were interested. Now, there's more theorists than just Higgs who predicted this. In fact, there are a set of 6 theorists who worked relatively independently in 3 groups that all came up with the same idea. And here's a picture of Peter Higgs on the right meeting one of those other theorists, François Englert from Belgium. And would you believe these people wrote their papers back in 1965, and this was the first time they had ever met in person. You'd think that would be impossible nowadays with the number of conferences and workshops and trips to CERN where people always meet each other, but they'd never met before. So there are many firsts going on that day for Higgs. Now, the reason it took us so long to find the Higgs is, as I say, it's incredibly rare. And let me show you how rare by showing you an animation of the signal from Atlas building up. So what you see here points to data. The red area is what we expect to see from things that aren't the Higgs. So for a discovery, you want to see an accumulation of data at a place, a particular mass that isn't described by the red curve. And you can just see it becoming apparent now. Well, that's more data than was used for the discovery. And just coming up now is our entire data set that's been delivered. There we go. There's a discrepancy. The next thing to do is to see if it's consistent with what we expect from the Higgs boson. Here in light blue is what we expect. It matches up. That's great. But it matches up within the statistics that we've been able to measure. And there's not many of them. And for that reason, this question is still slightly open. What we've seen, for everything we've measured so far, is that this Higgs is consistent with the one we expected in the standard model, but we can't be absolutely sure yet. And to test that, well, we do things like look to see how often we see Higgs in different experimental signatures. We compare that to how often we should see it from the standard model. We compare how often we should see it to how often we do see it as a ratio. And all these different ways of seeing the Higgs, if it is a standard model Higgs, should give you a point that lines up at 1. We see it as often as we expect to. You can see there's a bit of fluctuation. And you can see from the size of the horizontal error band, there's still quite a lot of uncertainty. And it's at this level we think we've seen the standard model Higgs. But we need more data to be absolutely precise, and that's going to come in the future. Now, I have to say that hasn't stopped people just working out things, just in case it's not a standard model Higgs. I had a look on the web at the archive where we put our preprints before our papers are submitted to journal. And I counted from the start of 2012 the number of papers with Higgs in the title. Now, bear in mind, there can only be a handful of experimental papers with Higgs in the title. I counted 1,946 papers, all due, well, the majority due to theoretical physicists coming up with really wacky ways in which this Higgs could be something completely different. Those are the sorts of things we have available to us to test. Okay, so for the first question, we've made progress, tremendous progress. We're pretty sure that the theory is correct insofar as the Higgs boson exists and it looks like the one we expect to see. What about the other questions? Okay, let's go on to the next one, antimatter. Antimatter is really investigated at the LHC by the LHC-B experiment. It's what it was designed to do. And I have to point out that the B in our name doesn't come for coming second or being second best. The B is there because we study the properties of the B quark, one of the fundamental particles. And we do that because, for reasons we really don't understand, the effects of matter and antimatter for that particular fundamental particle are most different. And that makes it easier to study experimentally. And that affects the whole design of the shape of our experiment. You can see from this cartoon that it's a very different shape to the Atlas experiment. And that's because B quarks, when they're produced, preferentially travel in the same direction as the beam. So we just instrument the area immediately around the beam. So this is a cone-shaped detector, where the collision between protons takes part at the left-hand end of the experiment. And we just make measurements of particles going forward. Now, to investigate antimatter and matter and their differences, the approach we take here is to isolate a sample of particles containing B quarks, like the B sub s mesons Josh was talking about. And we can do this from picking out a particular way that they leave a signature behind in our experiment, a signature that looks something like that picture, where in this case, the B sub s meson has decayed to two particles, a kaon and a pion. We obtain them from our data set, and then we subdivide them into matter and antimatter, depending on the electrical charge of those kaons and pions they've decayed to. And essentially, all we do is count how many of one we have compared to the other, because we expect B and anti-B quarks to be produced in equal amounts. So if we don't have equal amounts by the time they've decayed, that tells us something a bit strange is going on with antimatter, and it's that bit strange behavior that is what we want to understand. Now, as Josh mentioned, we made our first measurement of this difference earlier this summer. And here is an extract from the experimental paper. What it shows you is a number of B sub s mesons we reconstructed, we found out from our data. The matter version on the left, the antimatter version on the right. And the B sub s mesons, I'm afraid, don't correspond to the great big thing that goes off the top of the graph. They correspond to the little green area next to it. There's only about 1,000 of these things that we found in our data, despite looking at over 70 trillion proton-proton collisions to get them. That's why you need something like the LHC to generate the huge data sets for you to find them. It's very, very rare. Anyway, as you can see from the relative heights of those green peaks, we saw more matter than antimatter. And as Josh said, it was about 25% more. And that was great. So let's go back to our quarks and the difference between matter and antimatter. So we made a difference of it for made a measurement of it for the B quark. And it was a measurement that had a value of what we expected to see. And that was very good news and very bad news at the same time. I'll tell you what is bad news in a moment. And other experiments have investigated the B quark, the strange quark. LHCb can also investigate the charm quark, where we don't expect to see any differences between matter and antimatter. We can make measurements of that, and we don't see any differences between matter and antimatter. So that agrees with what we expect to see too, which is bad news as well. Now, why is this bad news? Well, the bad news is that we don't have an underlying theory of antimatter that gives us predictions for how it behaves that we can test to see if we're on the right track. We only have experimental measurements that matter and antimatter are different. And that means we have to describe this somehow in the standard model, because it's an experimentally observed phenomena. It means essentially we have to patch up this very beautiful, elegant theory with something quite ugly to just try and fit what we see. And the way that the standard model does that is by 4 numbers. It's quite simple. And of these 4 numbers, one of them directly describes the difference between matter and antimatter and matter, and the other 3 describe differences in quark behavior with the weak force, where we see matter and antimatter behaving differently, as opposed to the other forces where they don't. And we take all the measurements we ever made in any of our experiments that are sensitive to differences in matter and antimatter, and using our theory, we extract values for these 4 numbers from them, from our experimental results, and we compare the numbers that we get. So if these 4 numbers are a good way of describing antimatter, we should expect the numbers that we extract from all our experimental measurements to all match up and be consistent. If it's a really rubbish way of doing it, then they're not going to match at all, and that's going to tell us we have to think again. But in fact, what we find in this somewhat colorful plot is that it all works really well. So what you can see here are lots of different colored areas. These different colored areas are the allowed values for this standard model parameter that describes the difference between matter and antimatter from a huge variety of different experimental results, direct measurements of matter-antimatter differences, measurements of matter mixing into antimatter and back again, measurements of matter decaying, antimatter decaying. It all goes into here. But what we see is that all these allowed values coincide at one point. And that means that although there's no understanding, no deep reason to have this particular way of describing matter and antimatter in the standard model, it does the job. It describes what we see in our experiments really well. So perhaps that gives us a clue to its deep nature. Well, we can think about that, and we can look at the amount of matter we see around in the universe, and we can look at the difference between matter and antimatter that the standard model describes, and we can work back to see how much antimatter that implies at the start of the universe. That's a really good test. And what we find is that we don't end up with half a universe of antimatter. In fact, it's nowhere near that. We fall well short. We have found that we only describe something like a galaxy's worth of antimatter. And that's a problem, because we've described matter and antimatter behaving differently in the way we can test it with quarks. But this explanation does not explain how the universe evolved. We've made progress in understanding this question, but there's more to it. There has to be another way of tackling this problem. And indeed, there are other experiments that try to work on measuring antimatter in different ways to try and work out where the extra antimatter went. There's another experiment at CERN that isn't situated on the LHC. It's situated on an accelerator called the Antiproton Decelerator. Lovely name. And what this does is it makes samples of anti-atoms. You have antiprotons slowed down, cooled down in this accelerator, bombarded by positrons, which are anti-electrons, until some of them are captured into an anti-atom. And there's one experiment there called ALPHA that tries to hold these anti-atoms in one place for long enough to make some measurements of their qualities and their behavior to compare directly to hydrogen atoms. And this is the only way we have of looking at antimatter directly. But it's really tricky, because as soon as you make an anti-atom and it hits an atom, or it hits protons or electrons, it just annihilates. It's very difficult to keep it in one place long enough to study it. And what ALPHA have worked out is a way of doing that. They've made what's called a magnetic trap. It's very, very strong magnetic fields that can hold these anti-atoms in suspension by the subtle interplay between the magnetic field that's applied and the magnetic effects that go on inside the atoms. And that holds them in suspension. It stops them touching the walls of the tube and annihilating. And that means you can make tests of them. Well, so far, ALPHA has only really done a technology prover. It's managed to generate about 400 anti-atoms and hold them in one place for about 15 minutes. But it allows you to make some tests. You can test, for example, the effect of gravity on antimatter. I mean, this is a question. Does antimatter fall down under gravity, or does it fall up? Who knows? Antimatter is weird. You'd think it would fall down, but you really, really have to test it. And in this case, you can just turn off the magnetic field and see if your antiatoms float up to the top and annihilate, or just fall down and annihilate. Well, that test has been done, but without much in the way of statistical precision, and it will be done in the future with more precision. And also, we want to study the structure of antiatoms, the energy levels the positrons can have in them, compare them to the energy levels electrons have in hydrogen atoms, and so forth. And this is an area of investigation that's really going to start going next year, in 2014, when an upgraded version of this trap is going to be commissioned so that larger samples can be studied. And again, it's not the only handle we have on antimatter. These are just experiments on Earth. There's also a really good experiment out in space that you're going to hear about later on from Sam. It's the AMS experiment, and that is out in space looking for dark matter and antimatter. Now, there are sources of antimatter that we know about in space that just are a byproduct of protons moving around in the interstellar gas and scattering. They produce positrons as a byproduct, low-energy positrons. So we'd expect to see those. But there are other potential causes of antimatter. Dark matter may be annihilating. Now, that would be really good, because then we could understand maybe a bit more about dark matter, and we'd understand where extra sources of antimatter are in the universe that aren't described by quarks. You can have astrophysical sources that accelerate up positrons to enormous energies too. It's a really intriguing subject. And I was going to put the results here, but I'm not, because you can all wait for Sam's talk this evening, because I'm sure he's going to show you what they've seen so far. And it's really interesting. And the last way you can look at antimatter is a way we haven't managed to yet. I've told you about quarks. I haven't told you about neutrinos, because we know so little about neutrinos. And the next generation of neutrino experiments hopes to make the first measurements of matter and antimatter versions of neutrinos. That's in the future. OK, so antimatter, we're making progress, and there's many, many avenues of research going on. What about beyond the standard model? What about dark matter, my second big question? What about supersymmetry? Have we seen any evidence for supersymmetry yet in our experiments? Well, no. We're in the dark about dark matter still. And that's not for want of looking for evidence of supersymmetry to try and see if this theory is correct or not. Let me show you this list of investigations that the ATLAS experiment have done, looking for different supersymmetric particles behaving in different ways in the experiment. In each one, you see a colored line. That colored line corresponds to where we haven't seen that particle, where if it existed, we would have seen it. We've drawn a blank everywhere. So much so that when CMS, who also look for supersymmetry, presented their latest reports in an open report to CERN last week, they retitled this plot. Instead of calling it the CMS supersymmetry searches plot, they've called it the CMS we did not find supersymmetry plot. And here is their version. Again, the colored region showing you where we've looked for supersymmetry and not found any evidence for it. Now, just because we don't see it directly in front of our eyes, that doesn't mean to say it's not there and that we can't look for it in a more clever way. And we can also look for it in what we call an indirect way. And that's akin, let me give you an analogy. It's akin to flying an aircraft and just looking to see what's in the sky in front of you. You can look with your eyes at what's visible. That's direct. You can use radar to see what's hiding out there behind clouds. That's indirect. Well, we have our own version of this sort of indirect radar search for supersymmetry going on as well. And it comes back to this very popular B sub S meson. What we can do is study a very rare process where 3 out of every billion times this B sub S meson is produced. It will give us an experimental signature when it decays of a pair of muons. Very rare in the standard model. However, this rate can be enhanced or suppressed, changed about generally, by any new physics that's out there that can participate in this reaction. So that makes it a very delicate, sensitive probe of new physics, because it can reach out to higher masses than we can access directly. Now, with our entire data set at the LHC, LHCb and the CMS experiment have made their first measurements of this process, and it's bang on the standard model value, yet again. There's no smoking gun for a signal of supersymmetry. And this always makes the press, in Britain at least, get incredibly excited every time a new result fails to come out. And they have a whole variety of phrases and hyperbole that gets more and more extreme. So to start with, supersymmetry was being put on the spot. Awkward questions were being asked of the theory. And now it's got so bad that every time a new result comes out, we have headlines like, supersymmetry in hospital, supersymmetry badly damaged. But the point about supersymmetry is it's an immensely elastic theory, because there are so many unknowns inside it. What these results have done have ruled out classes of possible versions of supersymmetry, but by no means have they ruled out every type of supersymmetry. There's still much out there to test. And so because we failed to see supersymmetry so far doesn't mean to say that we're not going to be able to describe dark matter and that it doesn't exist. It just means to say that we need to go to higher energies to look further in order to find it. And of course, supersymmetry itself might not be the deep underlying theory of the universe that we've been looking for. Frank mentioned extra dimensions in the universe. We're looking for evidence of those experimentally. We're looking for evidence of new types of fundamental particles that we haven't thought of yet. We're looking for evidence for anything. And as you can see behind me, with all these colored lines, we haven't found any evidence of anything untoward or unexpected yet. We haven't even found evidence for the one thing we assured you would not be produced when the LHC started back in 2008. We've looked for them in our data, and we failed to find black holes being produced as well, which I must say is quite a reassuring thing. However, it doesn't really answer that question. Dark matter is still a huge mystery to us. The true nature of our understanding of the universe at this innermost level, this innermost frontier, is still a mystery to us. But research never, ever stops. So what I've shown you here is what we understand about the universe at the subatomic level, what our big questions are, our areas of uncertainty are, and where we've made our latest progress. But there's still more progress going on. What's happening now, although we're in a rest period with the LHC, is that we're performing maintenance on it so we can run at higher energies when we start up again in 2015. We hope to run at the design specifications, the design energies, and that will give us a much greater reach to look for supersymmetry and evidence of dark matter and evidence of really bizarre stuff that would be great if we could find something that would just show us where to look beyond the standard model. And it will also give us the extra Higgs events that we need to fully pin down whether that Higgs is a standard model Higgs or perhaps one associated with another theory like supersymmetry. Alpha and AMS are just at the start of their respective investigations and are going to continue to give us really interesting results that will hopefully give us progress in our understanding of dark matter and antimatter. And then beyond this, in the future, we're already thinking of the next generation of particle facilities. And this is important because it takes an immensely long time to design and build these facilities. You're looking at a lead time of something like 30 years from the decision to do something to the development of the technology to make it happen, the construction, the commissioning, to get to data taking. So that means that we have to plan now, even though we plan to run the LHC until 2030. And there are many, many, many discussions about what might come afterwards. But whatever comes afterwards, we're in a really, really incredibly exciting time, because we're in a phase of particle physics where almost every year we push the amount of universe that we're able to see, we push our horizons out further, where we can make more discoveries, or where we don't make discoveries, but in so doing, we just learn more about the universe and its behavior than we knew before. And what's incredibly exciting at the moment is we're just about to take another one of those steps by going up to full energy at the LHC. And we could find anything there, because it's in a part of the universe that we've never been able to study before. It's completely open. And I hope very much we'll find the answers to some of the open questions I've been telling you about. We may not. That's the beauty of research. We have no idea. So this is a subject in flux. You're going to have to wait to see how we push the frontiers of our understanding of the innermost universe out in the next few years. Thank you.
Thank you, Professor Shears, for that smashing talk. Sorry, I couldn't resist. At this time, I would like to invite our panelists to come up to the front, and we'll begin to collect questions from our audience. Remember, find an usher with a sheet to write your questions on, and then get them back to them. And we'll begin the question and answer period in a short time. Thanks.
Michael George Coyne, hi, nice to meet you. Thank you. Thank you. Thank you. You realize I'm going to pass all the difficult questions on to my esteemed theoretical colleagues? Oh, you're so nice. Thank you. Tara. Tara. But it's fine. Anyway, does it? Doesn't matter. Oh, no. Very good. Thank you.
Okay, folks, please find a seat, and we'll begin the question and answer period in just a second. Okay, Professor Mellema, you can start the questioning.
All right, we'll begin as always with any questions from our panel for Professor Shears. Anybody want to start? Jim.
I have a question. First of all, I wanted to thank Tara for a fantastic brief on what's going on at the LHC. It was just stunning. It was super, shall we say.
Absolutely.
Thank you.
A lot of people know that I wrote the first PhD thesis at MIT on supersymmetry in 1977, so I've been watching this idea forever in my life. And I noticed that on one of your transparencies, the one where you were talking about the decays of the Higgs, where you had the red arrow bars, there was one, which I believe was the Higgs go to 2W, where the red line did not line up with the rest of the data sets. Can you speak to that for the audience?
I can indeed. So how I would reply to this is that I showed 5 different signatures that Higgs leaves behind. And statistically speaking, if you look at how you would expect to see your data line up, that difference is completely probable. If you work out the probability of seeing that distribution, there's nothing wrong with it. It's not a sign that there's anything wrong. I mean, it might be interesting to motivate looking for it in the future, but there's nothing about that that says it's inconsistent.
Were those error bars 1 or 3 or 2 sigma?
1 sigma.
1 sigma. So yeah, that wasn't very far away from the line.
Yeah, that's
at
just
the, really 1.5
67%.
sigma.
I wanted to make sure that that point was made clearly to the audience for the eagle eyes out there watching the line.
As a theorist, it's even more important. There's an old maxim that no theory should agree with all the data because some of the data is wrong.
Sure.
Yeah. No.
I don't know that I agree with that.
But my serious question is actually this. You actually, in the latter part of your presentation, really kept returning to supersymmetry. And for a lot of people who follow the literature, the popular discussion, they keep hearing that supersymmetry is dead. So can you speak a little bit more about why, in your eyes, it was so important to come back and tell this more nuanced version of the story?
Well, it's impossible to kill off supersymmetry as a theory. And I said when I described supersymmetry, that was because there were a large number of unknowns in the theory. It's not very tightly known. There are many different values, different parameters in it can take, and that affects the masses of these new particles that are predicted. So they could be much more massive than we've seen so far. And that would still be perfectly allowable. Now, the LHC has ruled out masses, and that's great. So it's ruled out versions of those theories that predicted masses in that region, but it can't rule out everything. In supersymmetry, I must say, you must be very proud if it was your thesis. It's a theory that keeps on giving. You have predictions all the time.
But
I would like to mention that there is one bit of circumstantial evidence that's in favor of supersymmetry.
Is this the Higgs?
No. Well,
we know where he's going.
Maybe we should count that as 1.5. So I'll mention that also. That's good. Yeah. So when you consider unification of the forces of the standard model, which is based on strong electromagnetic and weak forces, all with different strengths, we'd like to unify those into one force that has just one strength, of course. However, as observed, they have different strengths. Fortunately, this phenomenon of asymptotic freedom that was mentioned predicts that the effective power of forces changes depending on what distance at which you measure them. And we expect the underlying simplicity and unity to emerge only at short distances. So you can calculate with the stroke of a pen how the forces will behave at much shorter distances. If you do that without including supersymmetry, the unification fails. But if you do it with supersymmetry, the unification works. So to me, that's very strong circumstantial evidence that supersymmetry is a feature of the physical world. Furthermore, the calculation relies on the supersymmetric particles not being too heavy. So I think there's an excellent chance that they will be found at CERN.
Frank, I'd like to thank you.
Also, I won a couple of bets based on faith in supersymmetry. Because before the Higgs particle was discovered, nothing was known about its mass. Its mass could have been, well, nothing is too strong, but its mass could have been anything, say, between 80 GeV and 800 GeV, an enormous range of possibilities. But supersymmetry predicted the mass would be on the low side, less than 150 GeV. So I put some bets at very long odds, like 10 to 1 against, that supersymmetry would be found at the LHC with a mass, the Higgs particle would be found at the LHC with a mass less than 150 GeV. And I won.
And now, if I may have my say, thank you. This is a commercial. You guys don't know this, but what Frank just did was give you a commercial for my talk.
You want to go first, and then, yeah, you got your
hand. Yeah, Tara, you expressed some relief that miniature black holes had not been found. But of course, even had they been produced, they wouldn't pose any danger to us for a number of reasons. And moreover, had they been produced, it would have indicated the possibility of an extra macroscopically big dimension. So astrophysicists would love this kind of thing, you know?
I do apologize. But I was quite relieved simply because of the fuss at the start of the LHC. And you're perfectly right. There's a really easy, logical way to understand that this isn't a problem with black hole production at LHC, because the energies involved in LHC, even though they're massive and much really energetic compared to other accelerators we've built, they're still tiny on the cosmic scale, and much, much harder interactions go on out in outer space. So if this is a mechanism, it would be happening all the time. But still, it makes our lives easier when we explain what we've done, just to show that that was right, and that's what gave me relief, even though I appreciate your concern.
I just wanted to add some to the play between Jim and Frank and Tara, that there's an interesting sociological phenomenon with experimental physics, which is usually wanting to try to prove the theorist wrong, and which is a good thing. But it's interesting that in the case of the Higgs, for example, before it was found, the amazing thing about the LHC and the machines before it is that it had ruled it out from all but a very small region. And I remember the experiment saying, we're going to show it's not there, you know. And of course, that was the region it was in. And so I think it's important to realize that the experimental non-discovery of supersymmetry will only be a non-discovery until it's discovered. If it's there. So it's really important to constrain it, but not having seen it is not the same as it not existing. And I think that's really important.
I'd like to make a related point, actually, broader, which is when you report that you're not discovering something, what you're actually reporting is that you're discovering that the standard model works extremely well, much better than its original evidence would have indicated. So we did well. And I mean, not only did we do well in formulating the theory, but enormous amounts of work and ingenuity have gone into calculating its consequences. And one wouldn't be able to make sense of anything that happens at the LHC without tremendous control on how things usually behave in the standard model, which usually means, as you mentioned, parts per billion or parts per trillion. When you're looking for discrepancies from the standard model, you're looking for very small effects. You're looking through enormous haystacks for little bitty needles. So you'd better understand hay very well. And it turns out that we do.
And in fact, as I know you're proud of, Frank, the thing you won the Nobel Prize for is now the background.
That's right. That's right. Yeah. Testing. There used to be an enterprise called Testing QCD, which was to test whether the theory was right. But now, after, well, depending on how you count, perhaps, I don't know, 10,000 sigma evidence in favor of QCD. Now we have pretty good faith in it. So now, instead of talking about testing QCD, people talk about calculating backgrounds. It's exactly the same activity.
There is one point. There's a point, however, if I may, that I think it's really important for Americans to understand. Okay. We salute the great triumph that took place at the LHC and with the discovery of the Higgs.
But I should point out, it's a triumph that belongs to everybody.
And I agree, and that's exactly where I'm going with my comment. On the occasion of my previous presentation here at the Nobel Conference, I spoke about the fact that we Americans stepped back from supporting something that didn't happen, which was the SSC, which you're very well aware of. The SSC would have operated at 3 times the initial design energies of the LHC, and a lot of the technologies, as you just alluded to, that go into the operation and the detection of the Higgs is made in America. However, it shows the danger of what bad choices can do when it goes out in the political realm and we look for questions where we ask the American people for their support in science. So there's a slightly cautionary tale here.
Actually, it's worse, because I remember when that happened, I used to think Congress was crazy.
Used to.
Professor Coyne has a question.
Could I ask Lawrence a question? Are they any crazier?
Oh, yeah. I mean, they seem like geniuses now. I mean,
if I may change the topic from supersymmetry, this smashing discussion, as Chuck said, of supersymmetry. I'm wondering, Sarah, it may have been buried in your talk, but I didn't hear it. Are WIMPs still a candidate for a fairly good fraction of dark matter?
Well, yes, they are. But we just haven't seen any evidence for them yet.
The lightest supersymmetric particle is a
It's
WIMP.
a WIMP, yes.
They're the one and the same.
Oh, I see. WIMPs is weakly interacting massive particles.
Yes.
Did I get that right?
Yeah, absolutely. Since the subject of WIMPs, can I chime in just a little bit here? Because a lot of us are real fans of WIMPs, and we don't mean the guys that walk down the streets, right? We mean the weakly interacting massive particles. In Frank's talk earlier today, he did something rather beautiful that I'd like to illustrate for the audience. He talked about inner space. Now, we physicists have been talking about this forever. We almost never talk about this to the public, and so this was actually a brave choice. But the thing that's really interesting that follows from this is that if you take the idea of inner space and combine it with string theory, you figure out that there are two forms of dark matter, WIMP dark matter and another form of dark matter called hidden dark matter. So it's rather interesting that this extension speaks to things that we still don't know about yet.
Well, I've got a question here from the internet that maybe accompanies that. This is from a Gustavus student named Jen, but she submitted it over the internet. What do you think needs to be done or invented before dark matter is something that can be discovered in the lab? And how close do you think scientists and physicists are to study dark matter in the lab?
Well, it all depends what dark matter actually is.
Yes.
So that's a very good question, and if I knew the answer, I would put bets on and then rake in the money.
People are exploring many different possible signatures or signals for dark matter. Professor Ting will tell us later about cosmic rays, which are one promising way, searches at accelerators. Another contender for dark matter that I'm very fond of, that I think is the best, actually, it's not a WIMP at all. It's this so-called axion that I introduced a long time ago, and certainly it has the best. It has a much better name than WIMPs. And important experiments to look for that are also being done that are quite different. They are more like the experiments used to search for the microwave background radiation and explore its properties. They use very special kind of antennas, because in some ways the axions are like photons, but more elusive. Then it's also possible, and in fact, such evidence, I should say, over the last few years, and especially in the recent couple of years, there's been one rumor after another of possible dark matter signals. And I think there are probably even 5 or 6 now, different groups that claim to have some kind of hint for dark matter. The problem is that these different hints all disagree with each other and basically rule each other out. But none of them has fit very well into any of the existing paradigms of dark matter, of WIMPs or supersymmetry or axions. So they're probably all wrong, but people are looking very hard for any non-gravitational effect of dark matter.
Let me say the other thing that makes it very exciting, and I may talk about this tomorrow, is that there's this competition because there are there's 2 ways to look for dark matter. One is to create it in the lab, as Tara talked about. The other one is to look at the dark matter left over from the universe, which is in this room, as I'll talk about. And that means that you can actually build direct detectors, and it's a kind of a neat competition because the existing direct detectors, some of which are underground, near here, in fact, are sensitive to almost the same kind of scale of physics that the LHC, that Tara talked about. And so there's this really neat competition. You don't know who's going to do it first. And anytime there's competition in physics, it's a great thing. Yeah.
Anybody else on the panel? I've got another question from the internet from Brad in Sioux Falls for Professor Shears about the LHC. He asks, what are some of the limiting factors in the energy produced by the LHC? Why is the design spec 13 TeV and perhaps probably not beyond that.
Oh, that's just a function of the engineering and of the magnets that we use to be able to control the beam and the devices that we use to accelerate the beam. Now, when charged particles go around in a circle, they actually lose energy. They radiate all the time, and it means that you have to keep on pumping energy into them, especially if you want them to go faster. And this has two effects. One is that you need to pick a type of particle that you'll be able to do that efficiently with, and that's why we use protons. But then that has a side effect. Protons are really hard to keep on bending round in a circle because they've got a lot of momentum. You need very strong magnetic fields to keep those beams going round. And when you have a circle of the diameter of the LHC. Now, why we run at 14 TeV was because that was the strength of the magnets that could be manufactured industrially at the time. It's the limit of the superconducting technology that was accessible at the time, which I guess we thank you for. But progress could be made if we could find higher temperature superconductors that are possible to manufacture magnets from at over the same scales, and that would help us push up the energy. The other alternative, and this is on the table for a future facility at CERN, is to build a bigger ring. Because if you have a ring of a larger diameter, then you could use the same strength magnets, but just make everything go faster. And people have already started making gestures towards the potential digging out of another ring at CERN that instead of being 27 kilometers long is 80 kilometers long, and it goes up completely under mountains and completely under the lake. It's quite speculative at the moment. But those are the only ways in which you can change your effective energy scale, and that's why we picked 14 TeV, because it was the limit of what was available.
And of course, that's why the SSC would have gotten to greater energies, because it was a much bigger scale.
Can I ask a question?
Of course.
Frank, you talk about axion. What is the most unique feature of axion?
Well, the axion is a very, very light particle. The theory has one parameter, so when I speak of axions, there's a range of possible properties. But given this one, it was like the Higgs particle before the mass was discovered. We know everything about it except one parameter, which could be thought of as its mass. But in this case, the mass, instead of being 125 GeV or thereabouts, is more like 10 to the minus 5 electron volts. So really, really small. It's a spin zero bosonic particle, very, very, very feebly interacting. And we believe, well, if you take the consequences of the theory, it would be produced in great abundance in the early universe in a kind of Bose-Einstein condensate that we could hope to detect as a relic today. Depending on what the mass is, you could hope to detect it either with appropriate kinds of fancy antennas, and that kind of experiment is underway at Livermore. They have a very ambitious program. But if the parameter is in another regime, very large, the most promising ways involve either looking for unusual effects around black holes, where axions could form atmospheres around black holes, or very sensitive magnetic resonance experiments that could detect.
Does it have a limit on its speed?
On speed?
Yeah.
But its speed would be cold dark matter. So the speed.
No. The speed would be faster than the speed of light, or less than the speed of light.
The speed of
axion.
Oh no, much less. It's cold dark matter. It's cold by now, so it cools off, and its mass would be just the mass of things that fall into the galaxy and are subject to its gravitational field. So 200 meters per second or thereabouts.
I've got one last question from the audience here for Professor Shears, which is there a project in the works at CERN that you're aware of to look for the force particle responsible for gravity?
For gravity? Oh. Well, the problem with gravity is that we don't have a good testable theory to make predictions to look how best to look for it. We do have some theories that are testable at the LHC, that, like the theory of extra dimensions, which can help explain why gravity is so weak in our four-dimensional space. by allowing there to be extra dimensions in space where it can be a lot stronger, and where we can see detectable experimental signatures from that feature. So we can test those models at the LHC, and although we haven't seen any evidence yet. Other experiments at CERN, I don't believe there's any others that are testing that sort of physics. There are other experiments at CERN that are testing antimatter, that are making very precise measurements of particular processes to try and deduce new physics beyond the standard model.
Well, I would have put it a different way. We do have quite a good theory of what gravitational effects should be produced at the LHC. It predicts you shouldn't find any.
Yeah, I mean, that's one thing we should really make clear that we maybe haven't, is that you sort of been implicitly said, and I guess once earlier too, that gravity is unbelievably weak. It's the first force we get to know of when we wake up and try and get out of bed. But that's because the whole Earth is acting on us. And in every particle sense, gravity is essentially irrelevant. The gravitational force between two elementary particles is so small, as Frank pointed out, that there's no conceivable laboratory experiment that could measure that. And that makes it very difficult because we have this really wonderful classical theory of gravity, and we'd like to understand if it can be made like the other theories as a quantum theory. But if we can't even test at a fundamental level the classical theory of gravity acting between particles, you can imagine how much harder it is to try and measure the quantum theory. And that's part of the conundrum of the forefront of physics.
But this alternative theory that would include gravity at the same level as the other forces also isn't at the level of sophistication yet to provide predictions that we can test elsewhere. So
it's very speculative.
It's undoubtedly wrong.
Well, nevertheless, as I mentioned, if there were at least one additional dimension that's macroscopically big at the 0.1 millimeter level, something like that, then gravity is strong enough to produce a black hole under the 14 TeV collisions that you hope to achieve. Yeah. So I mean, that to me would be a really fantastic discovery, because it would imply or suggest the possibility of extra dimensions, which are so important to string theory and everything, right?
It also demonstrates the complementarity, which I'm sure will come up in a number of times in the rest of these talks, between particle physics and cosmology. The universe is a laboratory, which is one of the reasons I spend a lot of time thinking about it as a particle physicist. And there are many experiments you can do with the universe that you can't do in a laboratory, and vice versa. And so the universe does allow us to test many things that we can't test at the Large Hadron Collider, the discovery of dark energy. And in fact, it may allow us to test, even at some level, the quantization of gravity, because the universe has certain properties. So that complementarity allows us to do things that's really important. We need both areas.
If I may, I want to make sure the audience is aware that there is a classical test of gravity underway right now. Everyone on this panel knows about it. It's called LIGO. It's a ground-based observation system where people are looking for waves of gravity. It's located in 2 states here in the United States, in the state of Washington and in the state of Louisiana. And so it's not that we physicists are sort of sitting back saying we can't test gravity classically at all. There is a test underway right now.
And to expand upon that, we're also looking for gravitational waves from the early universe, which will be another great test of classical gravity, but in fact, as actually Frank and I just showed, it may even allow us to test quantum gravity.
Yep. Actually, well, there are many tests of gravity.
Yeah.
Things fall down after all. And I mean, astrophysicists combine gravity in their calculations with quantum theory every day.
Yeah.
That's what they do. So despite a lot of loose talk, there's really no conflict between gravity and quantum mechanics. The conflicts arise only under much more extreme conditions than are practically realized or realizable in laboratories, or certainly most, maybe all, astrophysical situations. So you have to work very hard to find any evidence for quantum gravity, and in fact, none has been found so far. An effect that you couldn't ascribe to classical gravity. People have looked for all kinds of things. People have looked for fifth forces, and which would be significant deviations from Einstein's theory of gravity, and briefly found them, but those were discredited. People test very carefully, the equivalence principle, the perihelion shift of Mercury. Many, many experiments are done to test gravity. The people, modern cosmology is based on general relativity, so it provides many indirect tests of Einstein gravity. The trouble, if you want to call it trouble, is that Einstein gravity always works. It works very, very well. It's just like the Standard Model. And I don't think it should be considered as distinct from the Standard Model. It really is part of the Standard Model. If you take the Standard Model, it gives you a unique prescription for how you should incorporate gravity. That's the prescription we use, and it works.
Well, Frank, I would take issue with that. The back of the envelope calculation predicts a vacuum energy that's 120 orders of magnitude larger than what is actually seen. Right. Well, so I think that's the biggest error ever in theoretical physics.
No, but that's not a legitimate calculation.
No, it is, though.
The real,
it's the Planck scale to the 4th power.
The real answer that you get from that, the real answer you get from that calculation is no answer, because the ingredients that go into it are undetermined. So if you actually did the calculation, you'd find infinity, which definitely shows your theory has failed. In other cases where you encounter infinities, we invoke a procedure called renormalization, which sweeps them under the rug, which has succeeded in the past, and certainly, although it's inelegant, succeeds also in this case. I mean, you just, okay, so it's smaller than it should be, but if you take its value and put in that very small determination, nothing goes wrong. The theory still works. It's perfectly fine.
In fact, the canonical theoretical argument was that because it's infinite, it must be zero.
Yes.
Yeah.
Okay, folks, I think we're going to have to cut off the discussion at this point. We will have an opportunity for continuing the discussion after Alex Filipenko's talk at 3 o'clock. Thank you.